Good morning. My name is Christian Rothleitner. I'm from PDB, and I will chair the session, the first part at least. The second will be chaired by Stefan Schlamminger. And we have in the first part 3 presentations by Ian Robinson, Richard Green, and Shisong Li. And as this session is also participated by online participants and by people who maybe do not know this Kibble Balance community so well, I asked the presenters to give me a biography, and I will try to introduce the speakers first with a short biography. So each presentation will last 35 minutes, including questions and answers. And we will maybe allow 2 or 3 questions immediately, but please, if you have more general questions or specific questions to some of the presenters, please note these questions for the questions and answer session in the afternoon after lunch at 2 p.m. So let's start with the first presenter. It's Ian Robinson. He will talk about general considerations for building a Kibble balance. And Ian Robinson is an NPL fellow working on mass metrology at the NPL in Teddington in the UK. He joined NPL in 1976 and worked with Brian Kibble on the world's first Kibble balance, the NPL Mark I, which helped set the conventional value of the Josephson constant in 1990. Unifying the world's voltage measurements, he collaborated with Brian Kibble to design, build, and operate the NPL Mark II Kibble balance, which working at NRC contributed to the redefinition of the kilogram in 2019. In 2021, he was awarded the OBE, that's the Order of the Most Excellent Order of the British Empire, for services to measurement science in the Queen's birthday honours. Please.
Well, good morning, ladies and gentlemen. It's an honour to be here. I'm going to talk about general considerations for building a Kibble balance. And it's a big subject, so I'm not going to be able to cover everything. And also it'll be, I'll try to sort of not be too prescriptive about it, but I'll make some of my preferences clear. I'll start off by looking back at some of the development of the balance, just just to help understand what we'd like you to be doing in future. I'll cover most of the forms of the balance a little bit, but probably put most of the effort into the NMI type style balances, because that I think fits with the audience. And also I have to emphasize that there are many operational balances that work extremely well that have been built by not following any of the routes that I prefer. So again, all I can do is say what I think. Right, so just a little bit of history. That Brian Kibble, back in 1975, so 50 years ago, developed the first Kibble balance, mostly to stop himself having to work on the current balance. And if anybody's looked at a current balance, you wouldn't want to work on it. So, and it was aimed at replacing that, and it did. Brian had a load of contacts at NIST, including Ed Williams, and so NIST started building a balance very, very soon after we started. And the Kibble balance played a big role. It was called a Watt balance at the time, and it played a big role in unifying the world's voltage measurement systems by setting a conventional value for the Josephson constant. So you can see that the first balances were really fully aimed at metrological progress. Thing is that once we've done that particular piece of work, couldn't quite see what was going to go next. But luckily, Klaus von Klitzing in the previous sort of 10 years had discovered the quantum Hall effect, and that meant that we could effectively measure electrical power in terms of the Planck constant. And that meant we could link mass to a fundamental constant. So that looked like a good thing to do. And so that's what we set out to do in sort of around the 1990s, around 1990. The thing is that we didn't quite realize how difficult that was, because we needed to hit a target of around 2 parts in 10 to the 8, which was a lot more difficult. But again, we were heading, doing scientific stroke metrological progress. It was really heading towards a thing and not really heading out into any sort of industrial and other uses. The good thing was that a lot of other laboratories started to join in on the on this sort of piece of this work. Metas, I think, were the first to join, and we thought, wow, that they'll do it really well because it's going to be swift and it's going to be wonderful. But they hit just as many problems as the rest of us. So they're human as well. So we got through to the redefinition, but really once that redefinition had taken place, the emphasis changed. And so you've got the NMI level Planck balances, also Kibble balances, setting up a stable mass scale and providing mass at the highest level. But now it's possible to build and use industrial level Kibble balances. So effectively, there's a lot more people, a lot more interest in this work, but it isn't necessarily all aimed at science. It can be aimed at industry, all sorts of other things as well. So in some ways, it's become that the redefinition has really given people the sort of the license to go and do all sorts of really interesting stuff. Okay, so the NMI level instruments still work at the lowest uncertainties. They're still extremely difficult to build and operate, and you've got to have quantum Hall effect systems. You've got to have gravimeters, all sorts of things that are very, very costly. But if you're going for industrial level instruments, especially at lower uncertainties, you can measure mass, force, or torque. You can use conventional electronics, all sorts, but you're aiming at ease of use, low cost, and that's really changes the game a lot. I haven't got time at the moment to talk anything about the industrial force and torque systems. However, there's an awful lot of progress been made in those areas in the US, in Japan, and in Germany. So talk to the people who are doing that work if you really need more information. Okay, so how are we going to be using all these devices? For most of mass metrology, conventional mass standards are still going to be used. They're stable, they're low cost, they're easy to understand and use and pass around. Mass comparators still work very well. Their resolution is better than Kibble balance normally, and they're simple to operate, don't require expensive support equipment. So effectively, they're not going away. Kibble balances won't replace them, but it's a bit like the relationship between, say, cesium clocks and hydrogen lasers. They're both needed in the time scale, and these are both needed for the mass scale. And the other thing the one thing that should be noticed is that Kibble balances don't have to measure 100 grams, 200 grams, 500 grams, that sort of thing. They can measure any value with pretty much the same uncertainty. So it's possible to use a Kibble balance to measure awkward masses. And we saw an example of that from Stefan and from PTB and our people. They could measure a mass really well at a value very close to the first few digits of a Planck constant. So it's a niche application, but it shouldn't be forgotten. It's useful not to have to be able to measure anything rather than just 100 grams. Okay, the other thing is that we're starting to move to a point where Kibble balances will be allowed to make independent assessments of SI mass and distribute them to within their country or elsewhere. But it's important to remember that if you combine Kibble balances, you get a lot of gain. that you get a gain in uncertainty if they're independent, and reliability if, say, if one breaks, you've still got others to depend upon. You've got to be able to show that the balances are statistically independent, and the uncertainty of the average in a transfer mass will be lower than that of any single balance. So it's worth remembering that fact, though people can still will be able to just disseminate from their balance. But in order to do this sort of thing, the balances ought to be constructed and programmed to encourage the investigations that underpin their correct operation. So, because you have to show independence. Now, construction of balances, there are going to be issues in this area, I think, in the future, because we've moved from a research phase to really a development phase. And that means your funding may not increase, and it may make it difficult to retain good researchers. It's important under those sort of conditions that we think about keeping the complexity down, but there's a limit to how simple you can make a Kibble balance. It isn't a simple piece of equipment. So it's important that we move forward to be open, to make things open, reliable, and simple. And you need good support to detect and diagnose problems, because they can hide, silly little problems can hide all over the place in the Kibble balance. So go on to something that is one of my sort of particular likings, is simplicity and symmetry. I really think it's a good thing to keep the balance and as much of it as possible, as simple as possible. It means then you reduce the workload of people, perhaps because there's only one instrument doing a job rather than several. So you only got one calibration or one alignment or one something else. And also you've got less you can analyze the problems because there are fewer places where you're going to have to look. Unfortunately, there's a limit to the simplification. You can't do huge amounts of it because the balance is complicated. So, but if you can do as much as possible, it'll help. And sometimes you can also use symmetry in the design. If you're building Kibble balances, for example, if you place the mass in between the magnets, you put them in a magnetic, pretty much a gravitational null and a magnetic null, which gives you advantages in not having to calculate things to keep things simple again. So, and effectively the susceptibility of your mass doesn't matter quite so much. So again, to ensure that these machines work properly, you need to make sure that the parts of them are isolated and shielded, because you're making very, very precise electrical measurements in an electromechanical instrument. And you want to ensure that the parts you put together don't affect each other in ways you don't understand. And so if you don't control electrical interactions between those parts or other interactions between those parts, you're going to find all sorts of interesting second order and third order effects that you don't really want. So that really says you need to produce, for the electrical side, high quality DC and AC isolation, shielding, good power supplies, all sorts of things. Isolate the computer interface, and also don't allow low-level AC magnetic fields in your lab if you can possibly help it. Try it. We always specify for the lab, lab we use, that there are no looped mains cables going around it, because you get a lovely 50 hertz field going through the lab. Again, and then moving on, I'm going to move through this fairly quickly. The software of the balance, that's sometimes overlooked. Again, if you can simplify, it's a good idea. To my point of view, I like to see the controlling software small, fully understandable, so you can actually trace an action you're taking down to the lowest level in the computer. Not everything allows that, but I feel that's a great thing to do because it allows you to debug very, very quickly and accurately. Secondly, that you shouldn't acquire data and process it. It's much better to acquire it, throw it out in a standard interface, and then do all the processing separately. So you can use several different programs and make sure that all is well, and keep the thing that's acquiring the data simple. Also, you've got a balance that runs for days at a time. If you can't access it and muck around with it while it's running, sometimes you get real trouble. And I find the ability to interact with it while it's running and actually be able to change parts of it is awfully useful. Finally, I think it would be good, not necessarily that we'll be able to do all this, but if the software and the hardware is published in a free open source form, so there aren't any hidden parts. It again gives people confidence that things are working right and nothing is hidden. Again, I said a little bit about research, and I think that's one of the things I am a little bothered about, is that we've got to ensure that that we've got good researchers working on these balances, and if they're turning into machines that just do mass calibration, it might be difficult to do this. So again, we've got to try and maintain the expertise. So we need some interesting research, and that can be sort of smaller Kibble balances, also things like data analysis via AI and other things like that, so that we ensure that people are interested. Plus, there are things we need for the other balances, conventional voltage sources that are better than the present ones, and other things which actually have huge applications outside the Kibble community. I talk a little bit about industrial type balances, and I kind of what I've said is, if you've got uncertainties above 50 ppm, that means really you're aiming at masses that are very, very low. You can easily manufacture balances using conventional references. There is a region between that and the NMI balances where effectively you can go, but the cost starts to rise, because effectively you can't absolutely depend on conventional references to stay stable. And if you're going for industrial use, it's very difficult to tell an industrialist, you need to calibrate this this voltage source every hour, even. It's every few years they'll be happy with, even every few days, probably not going to happen. But a lot of people have worked in this area, NIST, PTB, and ILMA now. So things are being done there, and they're very successful. And you've also got to remember, when moving into the industrial space, that a conventional mass is awfully cheap, very good, and it's competitive to the balance in many areas. NMI level balances, they're for measuring 100 to 1,000 grams at the highest level. They're difficult to make. You need access to all sorts of very expensive equipment. So I'll move on to that. I just thought I'd go through the major quantities that we measure. Mass, before you were putting mass in, now the apparatus is pushing mass out. We measure velocity from the frequency produced by an interferometer, and we need the wavelength of a laser. Free fall acceleration is measured with absolute gravimeter, again, using laser interferometry. Voltages are measured using a Josephson array, resistance in terms of the quantum Hall effect. So one of the things you have to think about if you're actually starting to think about building a Kibble balance from scratch, how big are you going to make it? With the first NIST balance was up to 3 stories tall. And I remember it was wonderful. You could actually move masses around on the coils. It was great, but they are very big, and there are consequences to big. And it's noticeable, I think, that people are starting to move to smaller balances at the NMI levels. It saves you material, it makes things simpler in general, and things are easier to move around and modify. But you need to think very carefully about how you're doing that. In this talk, I'm not going to tell you how to do things, and just tell you what to think about. There's also a thing that NIST have labeled Kibble-Robinson theory, that effectively allows, if you build a Kibble balance in a particular way, which will be explained in more detail in a later talk, you lose a lot of alignment errors that you have to do an awful lot of work to remove in a non-conformant balance. So it's worth thinking very carefully whether you can take advantage of this theory, because it does help you a lot. Your choice of weighing mechanism is important. Many people use mass comparators, which is brilliantly good devices, but they normally, for this sort of work, have a restricted movement range, and so you can't adapt it easily to move as well as weigh over a long distance. So often you find that a balance with a mass comparator has a separate moving mechanism, and therefore you can't take advantage of KRT. All the other forms of balance can, but they all have their own advantages and disadvantages. You need to think a bit about the laboratory. So considerable thought should be given to this. Many people, obviously, you're given a laboratory, it's tough luck. But if you can meet some of these criteria, it really does help. Not having a floor that moves around is really good. And having basic temperature control is also, it makes all the setup things you have to do much easier. Now, vacuum or air, do you run the balance in vacuum? Do you run it in air? If you run it in vacuum, you get rid of air buoyancy, and the laser wavelength is the vacuum wavelength, which is great, but you've got all the problems of working in vacuum. Now, one group, UME in Turkey, have eliminated the refractive index problem using a little local vacuum, and that's a lovely way of doing things. But they then have to still measure the air buoyancy, but it's doable. But almost all the other groups choose to actually go into vacuum, which has a nice advantage of actually eliminating the noise caused by air circulation on the surface of the balance. It's a lovely thing to sort of see all that vanish. Now, moving on to magnets, I have to point out that a lot of this will be covered by other people in the next talks. I'm just going through it very quickly. So originally, NIST used a superconducting system to generate the field. At the moment, I don't think there are any other balances using that. BIPM style magnets are very popular, closed design, but can be split, and it shields the coil from external fields. Shisong will talk about that later on. And the NPL design uses two coils in a symmetrical manner, which I like, but the design is open, so it's sensitive to external fields. Also, what do? Do you move the coil or do you move the magnet? Many balances move the coil, a number move the magnet. There are advantages to moving the magnet because it's nice and easy to do, but you can't take advantage of KRT, and you've got to be very careful that external magnetic fields don't get in. Position and velocity, calibrated interferometers, you've got to choose between heterodyne and homodyne interferometers. I'm not going to say anything about that. That's a difficult area to make the choice, but and it's something you have to think about quite carefully. And if you use more than one interferometer, you can measure angles, and you can allow that can fix imperfections in the coil motion, but you'll end up with 3 interferometers rather than 1. And you've got to make the velocity measurement along the gravitational verticals, so you've got to be able to adjust the beams to the vertical. So voltage measurements, you need to measure the coil voltage and the resistor voltage to a part in 10 to the 9. But you've got to aim for a part in 10 to the 9, otherwise you won't hit a part in 10 to the 8. You can either do it directly with a voltmeter, or you can oppose most of the voltage using a voltmeter and then measure the difference of the voltmeter or nanovoltmeter. And again, that's a matter of choice. But the moving measurements do require special treatment because the vibrational noise from the measurement needs to be eliminated, so you need to measure frequency and voltage at the same time. The weighing measurements aren't anywhere near as critical. The resistor, you need to pass the weighing current through a resistor. You can either nowadays have a quantum Hall array or a conventional resistor. The quantum Hall array is wonderful, but it's expensive to obtain, needs cryogenic cooling and generates a magnetic field, all of which can be a bit of a pain. But you get an absolutely brilliant resistor. A conventional resistor, you have to have it, it has to be temperature controlled, all sorts of things. So you've got to be very careful if you're going to move it to be calibrated, that your temperature control, any part of it, it can't work out that it's been moved, because that's a really hard, it's an extremely hard error to locate. So to conclude, the design of these balances, I think hopefully you've seen from what I've said, it requires sensible compromise. You know, for example, there are loads of excellent low vibration environments in the world. You know, deserts, mountains can do it, but we choose not to build the balances there because basically no one wants to be there and you can't get the stuff there. I think that LNE once thought about building it in the middle of a mountain, but sensibly decided that that wasn't a good idea. So effectively, we have to then work in non-ideal vibration environments and think of methods to get rid of vibration, try and make sure that the pumps and compressors we end up using don't give us problems. So I hope that will give you an idea of what's going on. And if you are intending to build a balance, give you an idea of what you have to think about. But remember, simplicity and symmetry. Thanks very much.
So we will hear now a presentation about optical sensors and data synchronization given by Franck Bielsa. And Franck Bielsa received the PhD degree in metaphysics from the University of Paris 6 in Paris, France in 2007. He was a postdoctoral researcher with the Laboratoire National des Champs Magnétiques Intenses in Toulouse, France in 2008. From 2009 to 2014, he was a researcher with the Laboratoire National de Metrologie et d'Essai, Paris. He joined the Bureau International des Poids et Mesures, 𝐬𝐡𝐚𝐫𝐢𝐧𝐬𝐡 in France in 2014. He works primarily on the Kibble Balance experiment and is a member of the co-data task group on fundamental constants since 2021.
Thank you very much for this introduction, Christian. And I would like first to thank the organizer for inviting me to give this talk. Ah, the screen is not shared. Okay, sorry. Yeah. Just give me 1 second. Come soon. And yeah, that's this share. And I can go back here. Okay, now I think the screen is shared, right? Okay. So I'm going to talk a little bit about optical sensors and data synchronization on the Kibble balance. And first, I would like to emphasize with the audience with what I'm going to talk and what I will not going to talk. When we talk about Kibble balance today, we are talking about plenty of things. We can talk about the original operation mode of Kibble balance. We can talk about Joule balance. We can talk about Planck balance, which means compact micromotion Kibble balance. And each of these has very different specificities. So the point that I'm going to address mainly concerns, I would say, the top level Kibble balance in terms of uncertainty. So the Kibble balance operating at 10 to the -8 level typically. It is especially the case for the position sensor, which are related with the problematic of the alignments. And in terms of synchronization, I will mainly address the question of the original Kibble balance, which are requiring a very high level synchronization during the dynamic phase. Let's first have a small overview of the quantity that has to be measured in a Kibble balance. We first have what I'm calling main quantities, which are the quantities involved directly in the equation of the Kibble balance. So in the weighing phase, we have to measure the current flowing inside the coil, and we have to measure more or less synchronously the free fall acceleration. During the velocity phase, we are going to measure the voltage induced across the coil and the velocity of the coil. And for both phase, we need several kind of measurements. Some for the control. For example, we have to control the angular position of the beam balance, which is one of the important things in the control. And we also have to measure secondary quantities. What I'm calling here secondary quantities correspond to the quantities not directly involved in the Kibble balance, but necessary to determine some uncertainties or to analyze the data. It can be parasitic coil motion, so it is directly involved in the calculation of uncertainties. It can also be environmental parameters, such like the magnet or lab temperature and so on, which will be useful to analyze the drift and these kinds of things. So in terms of requirements for position sensors, the position sensor will be used in many of these measurements. The parasitic coil motion need to be characterized along the 6 degrees of freedom of the coil. 5 of them are there only for the determination of the uncertainties. That's inside the secondary quantities. And usually we are using relatively basic position sensors. But one, the second one is the measurement. The second one concerns the measurement of the angular position of the beam. Again, we can use more or less commercial sensors, but the largest requirements in terms of measurement concern the coil velocity measurement, because we need here to measure this with a very high accuracy level, at high resolution level, and it implies the development of a specific measurement system and of specific interferometers. So I'm going to talk about all this. In terms of synchronization, now, in the Kibble balance, we have different kind of measurements. During the static phase, we are measuring almost constant signal, the current inside the coil, the free fall acceleration. We are also measuring the environmental parameters. All these are very slow drift parameters. And usually when we talk about synchronization for these parameters, we are talking about typical synchronization at the second level, which is very easily accessible with software clock synchronization to UTC typically. So I will not talk more about this because it is something relatively trivial, I would say, in a lab. In terms of synchronization for secondary quantities, here, since the purpose of that is to easier the analysis of the data, and then to correlate the noise that we can observe on this, or noise or motion that we can observe on this with the main quantities, now we are requiring a measurement, synchronization, so we are at the millisecond level. Now it requires hardware trigger. I will describe a little bit how we do, but it is not that difficult to reach. The most important part of this synchronization concerns the velocity phase. During the velocity phase, the voltage induced across the coil and the coil velocity are perfectly correlated, since the ratio is equal to the geometrical factor of our system, of our voice coil system. And then a very good synchronization is required to take advantage of this correlation. Now we are talking about a synchronization at the microsecond level, and then we need a very specific synchronization scheme that I'm going to describe later. I prepared a short video, about 1 hour and 20 minutes. This is the typical sequence time that we use for full measurement with the BIPM Kibble balance. So we typically start with a dynamic phase without the mass. Now you are seeing the coil suspension on the left. I think I should use a pointer. Okay. On the left here, you see the mass. You see the mass pan. So the mass is on the mass exchanger. The mass pan here is moving. Okay. The coil suspension is moving up, and you see here the voltage induced across the coil, the velocity, and the ratio of them. And you see the synchronization between them, okay? That's the first part, the dynamic phase without the mass. Now we are going to proceed with the weighing, again, without the mass on the pan. So we are going to the weighing position, and then we start to measure the current flowing inside the coil and synchronously the acceleration, the free fall acceleration. Now we are going to put the mass on the pan, and we'll proceed with exactly the same measurement, but this time with the mass on the pan. So it takes a few seconds. In the real world, it is a little bit slower. Okay, the mass exchange is now finished. We go to the position of the weighing, and we are going to, we go to the position of the dynamic phase, to start the dynamic phase. And we are starting again a dynamic phase now with the mass on the pan. So we are measuring exactly the same thing. You can see on the right here the velocity and the voltage. They are both on the same plot, and the ratio is on the extreme right of the plot. So we are going to proceed with the same measurement now with upward trajectory. Okay. Done. And then we're going to proceed with the last phase of the measurement, which is the weighing with the mass on the pan. And of course, the difference between both weighing will give the equivalent of the mass. And we are almost there. That's it for the sequence. Okay. Now let's talk a little bit about the monitoring of the coil position. I should hide this, sorry, hide floating meeting. Okay, when we are talking about the monitoring of the coil position, we are not yet talking about the velocity measurement. So it concerns 5 degrees of freedom of the coil. 3 are the rotation around the 3 axes, X, Y, and Z. And the 2 other degrees of freedom are translation in the horizontal plane along X and Y axis. So first we have to measure rotation, and we have to measure this with a typical measurement range at the millirad level and a typical resolution at the microradian level. So this is something not that difficult to reach. And in fact, we can find a commercial device able to do this. Typically here I put 2 examples of commercial autocollimators that can be adapted in vacuum condition and so on. Of course, you can also develop your own autocollimator. It is not that difficult if you do not try to reach exactly the same accuracy that you can get with commercial system. In terms of translation, we are using almost the same kind of system. This time it is not an autocollimator anymore because the flat mirror here is replaced by a corner cube fixed on the coil, on the moving part that we want to characterize. And we just measure the parasitic displacement of the beam with typical commercial position sensitive detector or quadrant detector. Again, it is something that you can find commercially available. There are not specific difficulties in that. One thing that I would like to mention here is that for the translation, the parasitic translation are related to the velocity during the dynamic phase. And these sensors must be aligned vertically for purpose of velocity determination. I will not talk about the vertical alignment because Darine Haddad will do it in one of the next presentation in the second part of the morning. Okay, I can't move. Okay. Now we can talk a little bit about the synchronization of this parasitic coil motion. As I told previously, the requirements in synchronization are below the millisecond level, and typically these sensors are going to output a voltage. And a voltage is something that you can acquire with an acquisition board. Usually, the typical sampling frequency of this board are a few kilohertz or a few tenths of kilohertz. So if you just consider a kilohertz sampling, you take the triggers corresponding to the integration time of your voltmeters, typically. in the experiment. You just have to average out all these samples during the integration time, and you get your synchronization in a relatively easy way. Now I can give a few words about the measurement of the beam inclination. That is not for measurement purpose, but for control purpose. And we are talking about this, and you will see it with again in the Darine's presentation later on. We can talk about the two application of the balance beam in a Kibble balance. It can be used only for force comparison during the weighing mode, but it can be also used for both force comparison in the weighing mode and motion, and to provide motion during the dynamic mode, during the velocity phase. So if you are using your beam only as a force comparator, you don't need a very large measurement range because the deviation, the deflection of the beam will remain within typically a millirad, but you need a very high resolution, but you need a very thin control of the angular position for the force determination. So in this case, we are going to use typically as a position sensor shadow detectors or autocollimators. Again, it is something relatively easy to put in place or commercially available. Now, if you want to use exactly the same device to supply the motion during the dynamic phase, you will have to use an optical sensor able to measure over a large range, a large angular range, typically a few hundreds of milliradians. And this time you will need to use an optical interferometer, again with the same kind of resolution at a few hundred nanoradian range. But again, here you don't need a very high accuracy for your measurement. So commercial systems, such like, for example, AutoCube, but I will give other example later on, are perfectly suited for this kind of application. Now, since we started to talk about interferometry, we can move to the problematic of the velocity measurement during the coil motion. And here the things are getting much more complex because at the same time as the resolution, you will need an accuracy at the 10⁻⁹ level, since we are talking about main quantity of the Kibble balance. The measurement range will be typically a few hundreds, 100, a few hundred millimeters, with a measurement resolution at the picometer level, which is more or less the same as the accuracy required. And it is not that easy to find an interferometer able to do that. Typically in the community, two kinds of interferometers are used for this purpose. We have homodyne Michelson interferometers, or we have heterodyne Michelson interferometers. Just a short overview of commercial systems that can be found. Usually commercially available, you can find interferometers with plenty of operation mode, homodyne, heterodyne, frequency modulated, Fabry-Perot, probably much more than that, with very good resolution, high sampling rates, which is something interesting for synchronization purpose. Some are also available with low nonlinearities, but they are all limited in accuracies. Because some of them have anyway large nonlinearities because of the stability of the laser frequency. I put a few examples here of commercial systems. They can typically provide accuracies at I would say 50 ppb level, but below 50 ppb level, it starts to be difficult to find commercial systems. So let's now talk a little bit about homodyne interferometer. If we want to build an heterodyne interferometer, you first have to consider the accuracy. So you need to have a well-stabilized laser frequency at 10⁻⁹ level. And you need to consider the nonlinearity. And again, usually typical homodyne interferometer has large nonlinearity, sorry. But if you consider only integer fringe number, then the nonlinearity vanishes to 0, which means that if you want to use an homodyne interferometer, It is something possible with a drawback. You will only be able to count integer number of fringes, integer fringe number. Okay. And then, yeah, let me show you the kind of signal that you can expect at the output of an homodyne interferometer. So usually homodyne interferometer will output two signals in quadrature. If you consider here, for example, the black signal, this is typically a sine. The frequency of the sine is directly proportional to the velocity of the coil. And the phase, the integrated phase, simply correspond to the position of the coil. Is proportional to the position of the coil, and the sign of the quadrature will give you information about the direction of the motion. So all of this, I would say, give you all the information on the motion. And typically, if you proceed with a dynamic phase, the kind of signal that you are going to expect will be this one. So here you will see, okay, now the coil is stopped, it's speed up. Now it is running at a constant velocity. So typically the frequency that you are measuring here is something close to 5 kilohertz. Then the coil is slowing down and go back in the other direction. And this time you have exactly the same signal, except that you see the sign of the quadrature has changed, okay? So typically what you are going to measure during a dynamic phase will be, the parameters that you have to take into account are the fringe counting. So you are going to count every zero crossing and you are going to timestamp each zero crossing. The number of fringe will give you the position and the timestamp will allow you to determine the velocity. Now we can move to heterodyne interferometers. The principles are almost the same. There are some small difference. The well-stabilized laser frequency is still a base. Now we are going to use a double input optical beam in order to suppress the nonlinearity. And one important thing is that now, since we are allowed to work with a very low nonlinearity, we have access to fractional phase, not only integer number of fringes. And the measurement frequency is not centered on 0 Hertz anymore, but will be centered at 2 megahertz, which means that we can have something like continuous measurement with events occurring not 5,000 times per second, but with events occurring 2 million times per second. And then we will have a very small dead time in between two successive events. It will be something important for the following. So we have phase measurement almost continuous, since we have 1 point every 500 nanoseconds with a large sampling rate. This time, the position will not be directly the phase of each individual signal, but the phase difference between the two outputs of the interferometer. And then, because the frequencies are much larger than the one of an heterodyne frequency, the requirement in terms of timestamp will be much lower, so much higher, sorry. So typically at the picosecond resolution. So I can show you what looks like a typical heterodyne signal during one up-down sequence. So now the coil is stopped, it starts to move up. Okay, so you see the phase difference between the two signals changing. The coil will slow down soon, stop, yeah, and go back in the other direction. That's the typical thing that you have to analyze to determine the velocity of the coil. So again, you are going to count the individual fringe number. You are going to timestamp them. From the count, you can get the integral phase, so the position. From the timestamp, you can get the fractional phase, because you are going to do interpolation. And you can deduce the velocity. That's the two kinds of application that we have for interferometry in Kibble balance. And I think it is now done. Yes, and I still have time. So if you plan to develop an homemade interferometer for measuring the velocity of the coil, you have to consider first the accuracy of the laser frequency. Usually we are used to implement this with helium neon or neodymium laser stabilized on iodine transition. So it typically provides you a stability, a laser stability at 10⁻⁻11 level or even better. So it can't be something limiting for our purpose. You have to control the nonlinearity of your system. With an homodyne interferometer, for this, you are limited to count and to determine integer number of fringes. If you are using an heterodyne frequency, then it is more complex to implement, but you have access to the fractional phase, which means an almost continuous measurement. And if you have to choose between the types of interferometers, to be honest, I'm not able to say which one is the best one, but at least it must be well suited for your experiment. And typically, heterodyne interferometers are usually a little bit more complex to implement, but have one advantage in terms of synchronization requirements, and it is what we are going to see immediately. When we are talking about synchronization at the level, at the microsecond level, sorry, we have to consider different things. First, for an instrument, measuring something means that the instrument has to be informed that he will have to measure. Second, the instrument must be ready to measure, and third, the instrument must have a signal or an event to measure. Okay, so when we are talking about synchronization, we typically send an arming signal or triggering signal to the instruments, and then the instruments know that he will have to measure. Then the instruments need time to prepare his measurement, usually with typical TAs or acquisition card that we can use for frequency measurement. This time is very short, and then the instrument will wait for an event. So if you are considering an event with homodyne interferometer, every event are produced every about 200 microseconds, sorry, which means that between the triggering and the effective measurements of your device, you will have to wait at a maximum time, a maximum delay of 200 microseconds. So in the case of an heterodyne interferometer, now we are talking about events every 500 nanoseconds or 100 or 1 microseconds. And in this case, once you are going to trigger your system, you will have one measurement, one event within 1 microsecond. Okay, so in terms of synchronization, there is very big difference, major difference between homodyne and heterodyne interferometer. Which means typically that if you want to get a synchronization at the microsecond level, if you are using heterodyne interferometer, you can use external triggering. If you are using homodyne interferometer, you have to use the interferometric signal to trigger external device. So it is basically two different philosophies, and one consequence of this is if you are using multiple interferometers, must be synchronized together. Then you need something that you can trigger externally and that you can synchronize on an external system. And in this case, you have to use heterodyne interferometer. Otherwise, if you decide to use a single interferometer, you can simply use the interferometric signal to trigger other instruments, and then you have the possibility to use either homodyne or heterodyne interferometer. Now let's have a few words about the DVM synchronization. So in terms of DVM, Jan Robinson is going to present it in much more details in in the last talk of the morning. So I will not give too much information here, just to say that when we are talking about synchronization for digital voltmeters, high resolution digital voltmeters, we have not so much choice. The only commercially available digital voltmeters able to be externally triggerable from an hardware point of view, so below the microsecond level, is the 𝐬𝐡𝐚𝐫𝐢𝐧𝐠 3458, at least to my knowledge. So you have the option between these instruments or developing your own voltmeter, and in this case, you can manage the triggering more or less as you want. Jan Robinson will talk about homemade voltmeters. I will talk about the 3458. So typically on the 3458, if you send a trigger on it, the 3458 will require 100 or 200 nanoseconds to understand that you will have to measure something. And then you can expect from this kind of system a delay between the arming and the measurement at 100, 200 nanoseconds level, which is enough for our purpose here. I remind this is below 1 microsecond typically. And one more thing, a DVM usually require a time to measure and then a time to characterize internal properties and to save data. So if you want to proceed with a measurement, with a continuous measurement, you need to associate different DVM that you can trigger in cascade. And it is what is represented on the scheme here. So you have a typical sequence of trigger pulse, and each pulse are going to trigger one DVM. So here we start the measurement of the DVM1. Once the DVM1 is stopped, you start the integration on DVM2. When DVM2 integration is stopped, you start the DVM3, and at the end of the integration of DVM3, you restart on DVM1, and it is something sequential. Now a few words about the general scheme of synchronization with heterodyne interferometer. As I told you previously, heterodyne interferometers can be externally triggered. So typically you are going to use one pulse generator that can be made with FPGA, that can be made with other kind of device, to trigger synchronously all your timestamper, all your TAs, and all your TVMs. But if you do that, you can always trigger the beginning of the beginning of the measurement for the DVM, but you never trigger the end of the measurement, which means that in a second or in a first stage, you have to use exactly the same system to measure the integration time of the DVM, and then you can determine the best synchronization to synchronize all of your instruments. In terms of homodyne interferometers, now it is a little bit different. As I told you earlier, now you have to use the timestamp or the interferometric signal to trigger all the other elements of your system. So typically, you are going to acquire the timestamp and the events of your interferometers. It is going to trigger the pulse generator, and then the pulse generator will provide the triggers for the DVMs. There are also some other use. You can use interpolation, but yeah, for me, interpolation is not really synchronization. So since the purpose of this talk was synchronization, I will not talk about it. And I think we are almost at the end of the talk. So let's have a look on an example of measurement. It is the typical, a typical dynamic measurement that we can obtain with the BIPM Kibble balance, sorry. So that's one single trajectory. You have here the position of the coil. You have here the induced voltage across the coil, about 0.5 volts, and here the velocity, 1 millimeter per second. So that's the typical velocity phase that we can have. You see that on individual quantities, we have a typical noise or variation at the 4% level. Now, when we are doing the ratio, we got this. So that's our geometrical factor. And you see that the signal to noise ratio improved a lot because the synchronization essentially helps you to take advantage of the correlation between the two signals. And here you only have the correlated part of the signal, and the noise is the uncorrelated part. Now, if you look at the Fourier transform of these three individual signals, you see that the Fourier transform for voltage and velocity are almost the same here. It is almost impossible to distinguish the blue from the red point. And when you look at the Fourier transform of this time, the ratio between them, you see that the noise level has been reduced by a factor of at least 100 over the whole spectrum. And this is typically this kind of analysis that can tell you how efficient is the synchronization. Typically, in this frequency range, we have all the oscillation all the oscillation frequency of our coil and suspension. You see it perfectly well on the U and V quantities, on the velocity and on the voltage, but you don't see it anymore on the ratio. Again, here we have at about 12 Hertz, we have a broad noise, which is probably corresponding to ground vibrations, and we don't see it anymore on the ratio. With a bad synchronization, all this will typically remain on the ratio. In summary, so if you want to monitor the coil position for 5 easy to monitor degrees of freedom for what I called earlier the secondary quantities, you can get it with typical commercially available device, and it is not something that difficult to implement on a Kibble balance. You can use position sensors or collimators. For velocity measurement, you will have to get a measurement at a few ppb level to develop your own system. It must be accurate, it must be high resolution at the picometer level. You have the choice between homodyne or heterodyne Michelson interferometer, but any choice you make, it must take into account the synchronization requirements, and it must take into account the general design of your system. And that's it. Thank you very much for attention.
So our next speaker is Shisong Li from Tsinghua University in China. Thank you. Okay. So I also want to introduce Shisong. He has been working on the Q and Joule balance experiments since 2008. During 2008 to 2014, he worked in the Joule balance at NIM China. During 2013 to 2016, he worked at NIST on the NIST 4 Kibble balance. And during 2016 until 2019, he was a member of BIPM Kibble balance. Since 2022, he has been a professor in the Department of Electrical Engineering in Tsinghua University on the tabletop version Kibble balance experiments. So thank you.
Okay, thank you. So good morning. My name is Shisong Li from Tsinghua University. So I'm really glad to talk about this magnet coil design effects in Kibble balance experiments. I put Stefan's name here, so because we most of the containers are based on a review paper we wrote in some time ago. So I would like to, go through a few aspects of the magnet stuff in Kibble balance experiment. The first one is some very fundamental conceptions. The second one would be a very brief history on the Kibble magnet development. The third would be, how to design a good Kibble magnet system, right? And once you have the design, you need to make it into reality. Then you need to evaluate the performance of such a magnetic circuit. Then in the final aspect, I would like to talk about some systematic effects related to magnetic and some methods probably to reduce these kind of errors. So I think some audience, maybe not that familiar with Kibble balance principles. I just give you a very brief introduction, right? We have the winning phase. You put current into a coil. This coil is placed in the magnetic field. You generate upward, downward force, which balance the weight of test mass mg, right? You get mg equals BLI, and BL is some quantity. It's very difficult to measure. So then you have the velocity phase, right? You open circuit the coil, you move the coil in the same magnetic field. You measure the induced voltage and the velocity, right? By the U over V, you get this BL factor. So as we see, if we can keep the same BL factor in these two measurement phases, we can get like a virtual power equation. Like on the left is the MGV mechanical power, on the right is the electrical power. But the current we usually measure the voltage drop on standard resistor, or V over R. So then we can get the mass determination equation. So, but you don't see BL in the final, mass determination equation. But BL is very important to linking these two phases. So it's a highly clear, right? So if you put like a quantum standards electrical into this equation, you get a link between the mass and the Planck constant. So once we have the M expression, then we can write this, uncertainties, in a relative way. And as there's a two voltage measurement in both velocity measurement and in the winning. And think about it, if the BL is too small, right? You get a very low induced voltage, and then your U or V would be like have a larger uncertainty. If you, in the opposite, if your BL is really large, right, you need a very small current, then your current measurement have some uncertainty, right? So somewhat you can put these equations back to this uncertainty equation, and we get this relative uncertainty, two terms. One is proportional to BL square. The other one is inversely proportional to BL square. And of course, we can let these two terms equal, and we get the best in BL factor, right? This equals mgr over v square root. Of course, this plot shows a typical kilogram Kibble balance setup. So basically, if you set your velocity at 2 millimeter per second, use 100 ohm standard resistor, right? A kilogram, then you get like a best BL about 700 Tesla meter. So if you go to smaller range, or you use a lower velocity, a smaller, R, right? You can get different numbers. But typically, the best BL is ranged around 100 to 1,000. Maybe this range is good, right? Yep. So we know the Ohm's law, in electrical circuit, but we have Ohm's law also in magnetic circuit, right? So we know the Ohm's law is I equals U over R. But in the magnetic circuit, for example, I have an example on the left corner. You see this is a 1 per magnet PM, right? And then you have the flux will go through the yoke and then through a small air gap. And this can be, imaged into an electrical circuit. The PM is somewhat can be considered as a voltage source, right? Battery. The yoke, right, is the wire, and the air gap is basically the load. And we can also have these relations of these fundamental quantities, like the EMF to the MFF, right? The current to the magnetic flux, and the electrical resistance to the magnetic reluctance. And by definition, the magnetic reluctance is proportional to the length, right, along the flux, which is also reversely proportional to the sectional area and the mu as a probability. Look at the Ry, the yoke reluctance, because the mu is much higher, so you have a really low reluctance for the yoke. This is something, a wire has the same electrical properties, right? But if you look at the battery, this prime magnet, this reluctance is not that small. right? You have the LM, you have the same sectional area, and you have a mu0. Mu0 is more or less the it's comparable to the air gap. So in such a way, that means this battery has a very large internal resistance. So you have to remember that. But this, if we want to calculate the magnetic flux, you have to know the MMF, right? So for PM, I'm gonna not going too much details on the basic theory you can find in this textbooks, but we can write this. Just remember, this PM MF equals minus HC times LM. So HC is a perceivity of the permagnet, right? It's typically a negative value. And if you have a minus, of course, this would be a positive number. But if you can also write, if you write the phi with BS, right? The product of magnetic flux density times sectional area, then this S just gone, right? Then you have the B over mu, right? That is H. So you have H times length integral, equals to minus HC LM. So that's Ampere's law, right? So, but you should notice that, as I said, the internal reluctance for the PM is pretty large. If you double the PM, if you double the LM, I mean, your field will not double, right? Because the reluctance of the PM increase also twice, double, right? Okay, now you know some conceptions about magnetic flux, and magnetic flux density, right? So what is BL? What is really BL? So it's magnetic flux density integral along the coil wire. Okay, that's easy to know, but how can we understand this in this, for example, the BIPM type magnet circuit? So from the unit, we can just write add a meter in both lower and upper, right? And T meter square is basically the BS, right? So this is a phi. And on the lower is meter. So it is the magnetic flux change along some direction. Let's see, Z direction, right? So if you look at BIPM magnet, for example, if the coil sit exactly in the central plane, so because this magnet circuit has a symmetry, right? So in the center, all the flux is horizontal. So there's no flux lines going through the coil. That means the phi at this position should be 0, right? But when you move the coil down or up with position Z, for example, right? For example, on the right plot, you see there would be some flux going through the coil, right? But it's hard to calculate directly how much flux going through the coil, right? But you can convert this flux into some areas of this blue. You see this blue, circle, right? This surface, and in principle, all the flux going through the coil should, go through this blue, surface. And we know the inner yoke, the outer yoke, or at the coil radius, the flux is the same, but the magnetic field is different. So we can calculate this, flux, equations, just the BLZ. And again, if Z equals 0, it is 0. So now we know how to understand BL, in such kind of a magnetic circuit. Okay, virtual principle, I will not go too much because you can also find these conceptions in the physics books, right? So typically, we sometimes use a bifilar coil instead of single coil. Just for a general case, we write the energy of a bifilar coil, right? With 2 coils. It is the self-inductance energy plus the mutual inductance energy. The virtual principle tells you if you want to calculate the force of some direction, you just do the energy, change over this direction. It's basically the dE dZ term, right? But typically we have a minus sign there. But but you should be careful because once you have an external source, for example, a current source, right? If you keep your current constant, this minus will be plus. That means the source offers like twice the energy in the work, you know. You should be careful with this sign. But it gives the force with the inductance change over some direction. Okay, now I will stop with this conceptions. We go to the developed history on the Kibble balance, magnet systems. In the early stage, for example, the ampere balance, right? They use like a coil to generate such kind of magnetic field. And there's multiple ways you can like have a pair of equal, symmetry coils to have like a positive or negative current to generate some radial magnetic field. Then you have a single movable coil to generate the force, or you do the opposite. You have a single coil with some current, and you have a double coil with opposite connection to generate the force. And of course, you can swipe the positions of these fixed movable coils. But in general, we did a simulation. For example, if the number of ampere turns equals 200 ampere, this is a really large number, right? For a typical permanent magnet system, we have like a 20 something, right? So it's much less. But even with 200 ampere, you get like a magnetic field below 1 millitesla, which is really weak. So for the ampere balance, you can weight only very small masses. This system is not as efficient. I think in this NIST system is a nice system. They use the superconducting coils. That means you can put a lot of current into the coils, right? They use multiple pairs to compensate these variations of the profile. They can achieve like a really symmetry, flat, and strong magnetic field. But the drawback is, this has to be superconducting, and the operating cost is very high. So, and NIM1 is did this permanent magnet, system similar. It's equivalent, but such kind of system, there's no heating issues, but the field is also weak because as you see, this is a 30 something millitesla. And because it's also open, magnetic circuit, the uniformity of the material can affect the uniformity of the field distribution. Then it goes to a PM system, right? In the early stages, for example, the MPO Mark I system, they use like this, I call it a flat PM system, because it generates in the air gap uniform field, right? Then if you want to do the winning and the velocity, you probably need a 8-shaped coil, right? So I think the Metas I system also kind of adopt this kind of conceptions. Yeah, I mean, you should be careful because once you have a closed yoke and you with 0 ampere turns, but you have sometimes asymmetry during the mass on mass off for the current, so it still can cause some hysteresis during mass on mass off. You see, because even a small unbalance on the current could go through the yoke, right? And in the second improved design, they just cut the closed yoke loop, right? This case is much better. But in general, this magnet is you need to take care of these effects. So now we finally go to the radiant PM systems, right? And Ian Robinson already introduced some basic conception. Basically, the BIPM type magnet in the magnetic circuit or the MPL type. For this MPL type, you have like a 1 PM, right? It generate opposite field in 2 gaps, and then you have a coil with the opposite connection, and then you generate upward downward force, right? But this kind of magnetic circuit has some the shielding is not that good, But the next generation, right, they put like the magnet inside, right? This will reduce some flux leakage, in the outside. But there's a very, very nice feature for such kind of system is because they use a opposite connection for the coils, they can cancel out the electrical noise very nicely, right? If you look at the NPL measurement data, it's very quiet and you can amplify these signals, do a really nice measurement. And the LE system, they just, short, one of the air gap, right? So it's basically the same idea, but this system is not symmetric. That means it has a little bit weaker field on the top, right? And a little bit stronger in the bottom. I mean, the path in the yoke is longer. It's different in this case, right? But the LE, they did a nice, modification on their yoke, on their air gap wise. Their top yoke is 4 micrometer narrower, so they can compensate this gradient, right, field gradient, and in the end, they achieved a very nice, symmetry field. Well, the BIPM time, I think, it has some issues on the operation, which is difficult to close and open. But I think it is a very high efficient, very nice self-shielding and, very good symmetrical system. I think today, I think a lot of MIs use such kind of circuit, right? NIST 4, methods 2, NIM, CRACE, UME, Tsinghua University, they all use such kind of system. MSL has a very unique design, and I think this is just come from the flat magnetic circuit design, just to become radian. Again, you have to take care of the close the yoke loop issue. Like you add some small air gaps to cut this flux return, and this will of course reduce the field a little bit because of course you have additional gaps. Yeah, I asked Dr. Feng yesterday how to install this kind of ring magnet. It seems not easy. Anyway. Why do we need a radiant magnetic system? There's a lot of advantage. I think it's thanks to TP Olsen, right? NIST 3, and he pointed out that if the field is one-dimensional, what is one-dimensional? So you have only the R dependence, 1 over R, right? And then in the vertical direction, it's kind of uniform. Then your coil can be any shape. It can be a circle or a triangle, or you can tilt the coil at any angle. It doesn't affect the BL. For example, if there's heating in the coil, your coil is expanded and the BL doesn't change. That's a really nice feature, right? And also you should notice in the radiant magnetic field system, the BZ, the vertical components and horizontal components, they have a relationship. They are fixed by the Maxwell's equation. If you know the BR, right, you should in principle know the BZ distribution. Okay, the third part, how to design a good Kibble balance. First, we need to choose the good magnetic material, their general, the PM material and the yoke material. Right? For the PM material, you can choose a iridium material, but it can generate really strong magnetic field, but the temperature coefficient is a little bit high, right? It's about minus 1,000 ppm per Kelvin. But you can also choose, zero combo magnet. This temperature coefficient is lower, about minus 360 ppm per Kelvin, but you also have a lower HC number, right? Then you can, of course, use a very nice compensated, low temperature materials, but it will even, weaken the magnetic field. Yeah, so you have to balance the field and the temperature properties. Not means the iridium is not good because it in the meanwhile generates stronger magnetic field and you can reduce some, for example, heating, right? It has some composition. There should be some equivalent temperature coefficient. For the York, there's basically three kind of materials. For example, the NIST 4 system, they use a low carbon steel. And for BIPM, they use Super 50 is a very high probability York. And also you can use pure iron. I mean, I would like to choose like a high probability Yorks because in somewhat you can align the magnetic field better. But if you choose like Super 50, the material itself is quite expensive, right? But low carbon material is okay. Pure iron is cost affordable. As I think they're all good choices. Yeah. Then the next we need to define the magnetic strength in the air gap at the coil position. Then we can use this magnetic circuit Ohm's law equations, and we can just calculate the magnetic flux density at the coil position. And in the end, you will find some, constant over some two ratios. That means you have to arrange these two ratios in the same way, right? I mean, you have to balance these two ratios to get relatively strong in the magnetic field. Yeah. Then for a good design should have as large a uniformity range as possible, right? But as we have larger air gap, the magnetic field is getting weaker, but the uniformity range is decreased also. We found some formulas from literature, and they can describe very nicely the uniform range for a typical BIPM type magnetic circuit. As you see, when the air gap is narrow, for example, 5 millimeter, this is like 80% can be usable as the measurement range. But if the wise increase, this ratio gets lower and lower. Okay, how to improve that? I think if you look at the BIPM time magnetic circuit, these boundaries are not symmetric. On the right, you have York boundaries all the way, right? The green thing. But on the left, you have probability boundaries and also York boundaries. So in principle, if you put another pair of PMs in the outer York, you can fix this. And also, if you lower the outer York, it can compensate also, right? As you see, this is the magnetic field we did on a simulation. The first one is normal BIPM type. This one is with additional PM pairs, and this one is just lowering the outer York. It significantly improved the flatness. But also you can design some air gap wise compensation to achieve that, right? LNE, PTB, they also did such kind of composition. But the machining is not easy because it's a 4 micrometer machining, right? Especially after assembled is not easy. And also, if you have a asymmetry, well, you can do a composition. For example, NIM, they did a direct shunt, right? Use a very high saturation, flux density material. You just enter into the higher field this session range to short part of the flux, and it can flattening the profile. Also, you can use a very high probability Yorks, right? For example, the BIPM, they don't have the cover. This symmetry is not good, right? But they use really high probability Yorks, and in the end, they have nice symmetry on the profile, right? So this is also a very nice way. Of course, you can do inner York composition. This is some ideas proposed with Stefan some years ago. It's a very small change, but it can enlarge your magnetic field range very greatly. It's the same case, right? You see at 20 millimeters, it improved by like 50%. Of course, you can more different approaches to have that even better flatness. For example, the last plot is a merge of lowering the outer York and plus the inner York composition. Okay, next would be a splitting force, because for a closed magnet, for example, but for the NPL type, they don't have this kind of issue, but for the BIPM type, you have to insert your coil in and take it out, time to time. So you have to find a mechanism to do this. But generally, if you open this in the middle, it will be a repulsive force. But if your opening surface is going up, it become attractive, right? So somewhat you need to find some place, in the middle to make the force, manageable. So I'm not go too much details because it's already, yeah. For the Tsinghua system, we choose a nice, splitting plan, and with such kind of a system, when it is closed, the attraction force is a few tens of kilograms. And once it's opened by a millimeter or two, right, it changed the force direction. And then it becomes a really high, levitation force for the upper part. But you can really levitate the upper section by 40 millimeter, right? The space is not for you to insert your coil. And you probably see yesterday in the lab visit, I think the great merit is it solved the safety issue. You can put your fingers as you want. It never can hurt you because, your finger is always much larger than 1 or 2 millimeter. Yeah, you have to find the right device to install this kind of circuit. And we did some simulations for our compact magnet system. But it can still reach like 6 kilonewton force during the assembly, right? It's a lot. But you just need to find the right range force suspension. For the temperature, you can do a temperature composition like Metas did. The idea is you insert some shot with a very high temperature coefficient. That means the probability change largely on the temperature. And they did a really nice composition. But we also tried to do some composition for the Neuridium version, but it's very difficult, Yeah. Maybe for small temperature coefficient, you can do this composition. The idea is just simple, right? So once you have the magnet, you need to average the performance. First, you need to measure the profile, right? I think the NIST team proposed really nice, methods, the gradient coil method to do this. You basically measure one coil measuring the large signal, the other two coils connected in the opposite way. You measure the differential signal, and in the end, you get very nice profile measurement. This is a comparison with a direct U/V ratio to the gradient coil. We can see very clearly the profile with very high resolution. Okay, you now measure the profile. If the profile is not flat, of course, you need to go through the composition thing, right? For example, you need to modify your air gap wise a little bit, which is not that robust. This is you probably do several iterations to get there, or you never get there. Right? For example, the NIST one, we did several modifications. It's not that successful, but in the end, we find a shaping method. This is quite nice. The idea is we have this splitting device, right? We put at some point shaping, and then we close it. Then we create in the opposite direction a saturation point, right? Then we slightly open the splitting device and change the shaping position, and then you see the profile is getting flatter and flatter. And if you open completely the magnet, it will reset the profile. So in principle, you can choose the profile you want by shaping. That's a nice way. Of course, you can do some magnetic York compositions. I will not go details about this. I already talked somewhat, And then you need to, sometimes for the magnet moving mechanism, you need to average the shielding performance of the magnetic circuit, right? So you cannot measure directly inside the magnet because it's a sub-Tesla thing. You try to measure within like a 8 magnitude. It is impossible with magnetic sensors. So what we did is we removed the PMs, in the magnetic circuit. We put like a weak field sensors, and we place some, external flux, to see how this field are reduced, at the coil position. And it's found that this reduction is like very, very nice. And then in the end, we are going to monitoring the external flux around the magnet, and then we know the the ratio, how the field is reduced, and then we can merge these two factors and get some evolution on the systematic effects. I will not go details, just go through our paper and check. Of course, once you have the magnet, another thing you need to check is you need to meet the alignment requirement, right? You physically move the coil horizontally, then you see some tilt, right? And you should, in principle, find a minimum, a point of tilt for both X and Y axis, right? This is something you need to check. Our temperature, you can just measure directly or use the winning profile measurement. So systematic effects, this is the major challenging part, right? So basically, the current effect, you have like two terms, the linear and the quadratic terms. So, of course, you have high order terms, which is not important. So for the linear term is mainly caused by the coil self-inductance, as we already know the force calculation equations by virtual principle, right? We get this winning BL change during this inductance force and the I ratio, and is basically I over 2 dLdz, and you see this is proportional to I, right? And if you do experiment, you will find the inductance of the coil is a quadratic distribution at the along the vertical direction. That means you have a minimum, a maximum values in the middle, and this corresponding to some negative slope force curve. That means if your coil is moved up, this force will drag it back to the center, right? The lower is the same principle, right? We did a lot of measurement to model this kind of experiment effect, right? We see this very clear. This is a linear linear function to the I, and this can be calculated or measured. Just the additional, I think Hall already introduced it yesterday. If you use a bifilar coil, use one mode measurement, you will find this current effects. These dashed lines are the waning muscle on muscle off, and this solid curves from the velocity measurement. I think Franck showed the video. You see this profile is sloped, mainly due to the current, and you can theoretically prove that these slopes has a relation of effective 2. So it is really good supporting you to do the data analysis, right? To remove all this kind of current effects. Yeah, but how can we measure the alpha? Yeah, there are several ways you can do a direct different frequency exponential, right? You use the standard resistor, and you measure the voltage on the coil and the standard resistor and do some calculations to figure out the phase delay, the amplitude, and then you do a linear fit on the frequency dependence, and you can find the DC values. Of course, you can use these BL changes in the winning and velocity, right? You can put some constant current. You can move the coil in the range. You monitoring the induced voltage, and you get this alpha value. And you can also do winnings at different positions if you know the profile. There's several ways to do that. But where's the bias come from? It's mainly due to the coil position change during muscle on muscle off. Your coil, your mechanical system will be stretched. There's some deformation, and this will cause some displacement for the winning positions on muscle off, and this will generate a considerable corrections for your BL value. And we did a calculation on the BIPM system. It is 10 ppb per micrometer, which is significant. A dynamic effect. And because you see the current effect, there's different slopes in different winning phases, muscle on muscle, right? If you know the diamagnetic force mechanism, right? For example, you put some frog into a very strong magnetic field and has a gradient. So the frog will just fly, right, in the magnetic field. But if we have a slope, but we also have in the meanwhile a considerable B value sub-Tesla, then this force will not cancel out during muscle. It is close to 1 ppm. This is a huge effect. It took us about 2 years to understand this, but in the end, we finally understand that it's not a problem. It's not challenging the principle of a Kibble balance measurement, right? So we find in the velocity the similar effect, and it's in fact very symmetrical equations at the PPP level, and we are safe. We are continue to use these measurement principles. What we did is some amplifications on the chi values, and you see this current effect. You can also see these diamagnetic effects. Yes, you need to make corrections for the chi, for the magnetization effect. And this everybody knows. But yesterday we talked with, there's 3 rows through a huge, magnetic gradient, at the hole, the magnetic hole positions. You have to take care of this position change during the muscle on muscle. Probably can generate some effects because the gradient is so large, Okay, nonlinear effects. I will not go details. I can just tell you we are safe, for York nonlinearity, for the hysteresis effect. This is interesting, and we did the evolution of BIPM system with 2 Yorks, one without heat treatment, one with heat treatment, and this one without any heat treatment is smaller, and you can understand this because without heat treatment, this hysteresis loops is very narrow, so you can simply it's more close to a linear system. So once you have your York heat treatment, is like there's a nonlinearities, right? What we did is we amplified these errors and tried to see the values at the small delta H change. Thermal effects. Of course, if you use a two-mode two-phase measurement, you have heatings in the winning, and you don't have heatings in the velocity. This will generate some ripples on the temperature, and then a BO change, of course. And we find that this effect is significant for compact magnet systems. It's proportional to P-8. What is P? P is a one-dimensional scaling factor related to some system, for example, NIST-4, right? If your P equals 0.5, you have like 1/8 of the volume or the mass of the NIST-4 system. But this is a increase like very fast if your magnet goes small. We did simulations, and also we did some experiment to test these effects. But generally, if you use one mode measurement, it can suppress this effect by a lot, right? Then you can even further change the ramping strategy to have even better result. Details, go to the papers. Okay, so we can summarize these different effects, and for different p-values, you see this thermal effect is really the major one. And in fact, set boundaries for your magnet size. If you want to reach 10 ppb measurement uncertainty, your magnet should not be smaller than some value, right? We give this result based on experimental measurement. Okay, summarize. We have talked a lot, I think, tabletop small compact magnet design would be very important for everyone. it's not only you build a magnet, you need to investigate all kinds of systematic effects, related to the measurement. I just give you some updates on our magnet design. We now have different versions of a Kibble balance magnet BIPM type, but with some new features. We would like to open hardware these systems. Is anyone get interested in such kind of system? Just contact us. We can offer you the drawings and designs. Yeah. I think that's it. Thank you.
So this is the second part of the special session on knowledge transfer. And it's my great pleasure to introduce the same old Richard Green again. He is a senior research officer in mass and at NRC Canada. And since 2011, he has specialized in precision mass metrology in air and vacuum and contributing to the high accuracy measurement of the Planck constant that in the end led to the redefinition, and is now working on the realization of the kilogram using the NRC Kibble Balance. He's the vice chair of the Consultative Committee for Mass and Related Quantities Working Group on Mass, and is a member of the CCM task groups on the phases of the decimation of the kilogram. The floor is all yours.
Okay, thank you very much for that introduction, and thank you for the opportunity to give this talk, and thank you also to Frank for being quick on his feet and taking over my talk slot when my presentation didn't go through. So yeah, so today I'm just going to talk about the mass and gravity related to the Kibble balance. And so as an introduction, I'll talk about the process for disseminating the mass from the Kibble balance and the transfer mass selection. So this is the artifact that you use when you're doing the realization. So I'll use maybe the realized mass or the transfer mass interchangeably through the talk. I'm going to talk about some considerations for vacuum to vacuum transfer. So that's going from one vacuum environment to another vacuum environment, often in this case through air in between, and then talking about vacuum to air transfer. So in the end, what we want to do is you want to take the mass that's realized generally in vacuum for the highest accuracy balances at the moment to air where it's disseminated out globally. So the purpose of all the presentations today is to really nail down the realization of mass. And it's effectively a mechanical, electrical, optical project. But in the end, we're realizing mass, and it's the purpose of it is to do mass. And so what we want to do is be able to get that out of the Kibble balance into the hands of the users at the highest accuracy possible. So next thing we'll talk about is the gravity. So both absolute and relative gravimetry, the associated tide models, which is related to the daily variations, and then the gravity transfer, which is moving from one position to another position in the lab. So how do we ensure that mass realized in the balance, in the Kibble balance, is the same as the one disseminated out to the world? So all the hard work we do will be transferred directly over and give benefits to everybody else. So this is typically done in about 3 steps. Right now we have the step 1, which we start, say, in a Kibble balance. This is the NRC Kibble balance. This operates in vacuum. I'm not going to talk about Kibble balances that are operating in air for the purpose of this talk, but there's masses that need to go in there, then they need to be transferred out into the world. We usually do this through a vacuum balance, and which I'll talk about in a little bit. And then step 2 is we typically will transfer that value off to participate in the key comparison of realizations, which is what currently is used to provide the consensus value of the kilogram and calculate that value with, and then that will come back from the BIPM at the end of step 2, and then we can use the same value to disseminate out to stainless steel in air. So that's where we do the vacuum to air transition. So both the realization here and the comparison here is done in vacuum, but the end user is all in air. And so we'll talk about how we transform that. So for us, we need to select a particular mass that has suitable properties for utilization in the Kibble balance. And because it's an air vacuum transition, there's something that we need to think about as we do those measurements. And so you want to have a mass that's very stable across those vacuum environment to a vacuum environment, vacuum to air environment. And the way you ensure that is in principle by keeping the surface area very low. So all the changes that happen on a mass typically happen at the surface. So it's a surface mediated process. So all things being equal, you want the surface area to be as low as possible. And that means having a mass of highest density possible that allow you to do what you need to do, and then have a lower roughness value. So the smoother the mass is, the lower the surface area is as well, in principle. So typically you want to have a shape where that surface area is minimized as well. And we use cylinders typically where the height equals a diameter, and that's the minimum surface area for those cylinders. And then of course, if you use a sphere, then that's basically the smallest surface area you can have for a given mass. Depending on the residual magnetic field of the balance. So all the Kibble balances, as you've seen, have a permanent magnet associated with them, and the ones now are mostly shielded, but there's in some of the balances, particularly the one at NRC, we still have a residual field that we can see it where the mass is placed on the weighing pan of our Kibble balance. And so what we need to typically consider is the magnetic susceptibility of the mass. You want to pick a material that's got a low susceptibility depending on the field, the residual field at your mass pan. So if you have a low residual field, then it really doesn't matter. You can use stainless steel or platinum. These are standard materials. If you have higher fields where it might be significant, you can use diamagnetic materials like copper and silicon. And we've also used tungsten. And tungsten is actually quite good because it's relatively inexpensive. It's very dense and it's very hard. There is a complicated oxide structure on there, which might make the sorption a little bit more difficult sometimes, but so far we've had good experience with it, and the stability has been pretty good. So what we can do is the susceptibility of the mass and the uncertainties associated with the susceptibility of the mass is dependent on your magnetic field. And so we've measured the residual fields near our mass pad, and we can do corrections for that, and we can all do those corrections if you know the field. And this was just measured with a Hall probe around the mass pan, and this is the equation we use to do the calculation. And these coefficients are just related to the form of the field. But approximately, you can approximate it just based on the change in the gradient on the top of the mass to the bottom of the mass if you're using a cylindrical mass. And because of our field has got this sort of parabolic shape, we can find a minimum position. We can adjust the height of the pan to be in the position where the gradient is very, very low between the top and the bottom of the balance. But we have some adjustments, and that because where you start and where you end will depend on the identity of the mass or the height of the mass. We've kind of taken one that's in the sort of the area we want to use, but then we make approximations or adjustments depending on the actual heights of the mass. And so typically, this has just been modeled with a cylinder of about 52 millimeters, which is the typical stainless steel 1 kilogram. And you can start hitting about a microgram of contribution, or 60, 50 microgram of correction at about 10 to the minus 3 on your susceptibility. So that's typically around stainless steel. You can maybe get a little bit more. Tungsten is around 10 to the minus 5. Platinum is around 10 to the minus 4 on that order. And then silicon and copper are diamagnetic, and so they're negative, but in parts in 10 to the 6. So how we do the mass comparisons is we do the Kibble balance measurement. We have that transfer mass that goes from the Kibble balance to our vacuum balance, and the vacuum balance then can compare that to all other weights that are stored in vacuum. What we have, this is the 2 vacuum balances commercially available that exist right now, and they're incredibly good balances. It's amazing. The resolution is really, really good. Operates at 1 kilogram. Balances are nice because they're just differential measurements, not as hard as a Kibble balance, which is an absolute measurement. So you're always comparing two weights with each other. Typically, the uncertainty of the weighings are less than 3 micrograms. It's not so hard to get 1.5 micrograms. And you can operate the balance between 10 to the minus 6 millibar and 1,000 millibar. We've even gone over a little bit and pressurized things. And so we use this for comparing masses in vacuum, as well as for transitioning from vacuum to air for our mass scale. So the question is if your vacuum environments are different, so between your vacuum balance and your Kibble balance, you want to make sure that the values that you're measuring to disseminate the value that you've gotten in the Kibble balance is the same as the one that you're carried into the vacuum balance, and they're disseminating out into the world. And so this is work done by James Berry and Stuart Davidson from NPL, where they just did vacuum cycling on various samples at different pressures. And it turns out that as long as your vacuum pressures are typically below 10 to the minus or 0.1 Pascal, then you more or less have a reproducible change from air to vacuum. So reproducible value in vacuum on your masses. Silicon does some funny things at the mid pressures between ambient and 10 to the minus 1, but in the end, they're fairly close to 10 to the minus 1. There's some surface chemistry reasons for that that's described in that paper. But so that means that these measurements are all done in the same vacuum chamber. So it's not so unexpected to see it quite repeatable. What becomes a bit more challenging is when you're in vacuum, you go to air, you move things around, you move them into a different environment. And so this is Stuart also did these measurements previously where he's compared masses in air and in vacuum and looked at the transition of the mass change on the mass that goes from air to vacuum. And so you can see over time, this mass that went through vacuum to air, vacuum to air, vacuum to air multiple times, it gained weight in time. And typically that was on the order of 2 to 3 micrograms. And we see this as well sometimes when we're going from our Kibble balance, our vacuum balance to the Kibble balance and back again. And it's not always reproducible, but it's something that needs to be considered. And so generally what we always try to do is we measure our transfer mass, the mass that we want to realize the value on. We compare them to a bunch of other stable masses that have been stored in vacuum for a while, and then we cycle them back and forth a few times to see how that change happens. And then we can make corrections for it when we go to the Kibble balance and come back again. So in this step 2, that's when we're transporting the mass out to participate in the key comparisons and to provide data for the calculation, the consensus value. And again, doing all the hard work on the realization and then sending it to the BIPM and having it change mass just through transportation. This is something that you want to minimize. And over the years, we've done quite a few different enclosures for transporting it. So how do we enclose the mass when we ship it to the BIPM and back again? And so these are the old enclosures for platinum prototypes. This one is from NPL, and these ones are all in air. And I found we've had variable success with these, of about 7 micrograms change coming back and forth as the highest. And to the lowest, we found these ones, which are hermetic enclosures. So if you want things to be in the same lab air for as long as possible, and then so you only have small transitions from the environment in your laboratory to the environment in the laboratory, the BIPM, not worrying about all the possible environments that you might get on the way to transport things. So on the plane or the shipping department and whatever else. And so that's worked very well for us. So these are our drift values going from NRC to the BIPM and then back again. And so this change from here actually goes right into the uncertainty of the realization when you're taking the key comparison results. That goes directly into your uncertainty, and so that needs to be considered. So now typically we get quite good results, and we've had that for the past few key comparisons. Now for step 3, we've got the mass back at NRC and we have the realized value effectively in vacuum. What we want to do is we want to take that value from vacuum to air. And so in vacuum, there's a different amount of stuff on the surface. Typically you'll have, when you go from vacuum to air, water will absorb on the surface, hydrocarbons will absorb on the surface, and that changes the mass. And so fortunately, all we need to do is we need to take masses that have very similar surfaces per unit area, but then make a mass of minimum surface area and compare that to one of high surface area. And we presume that all the surfaces act in a similar way. So they behave a similar way when they go from air to vacuum. The interesting thing is you can kind of have as much sensitivity as you want for that measurement going from air to vacuum. So the way we calculate that sorption correction is just we measure the difference between the two artifacts in vacuum, and we measure the difference between the two artifacts in air. And there'll be the stack will absorb much more mass than the low surface area one. And then if you take the difference between those and you divide it by the difference in the surface area, you can get the sorption correction or the value of the sorption. Then you just multiply it back by the surface area that you want to correct for. The one thing that we need to consider in this is, how do we know that the surfaces are the same for your stack and your integral masses? One is mostly a curved surface and the other one is mostly a flat surface. But what we've done is done comparison where there's 3 sets of sorption artifacts were used to measure the sorption correction on a platinum iridium prototype. And we did this at NRC, at the BIPM, and we used NPL artifacts as well for doing this sorption correction, and the value came out very, very similarly. And this is all over many years. So the sorption correction seems to be fairly stable and repeatable, even using different artifacts. So that gives some evidence that it's quite good. The sorption values vary depending on the material. They also vary depending on the cleanliness of the material. So if you have a mass that's older and has got a thicker contamination layer, that tends to interact more strongly with the environment. So it'll tend to absorb more water and you'll tend to have a higher sorption correction for older masses. But if you didn't have a vacuum balance and you wanted to go from vacuum to air, and you just wanted to guess the sorption correction, we have kind of enough data now that you can probably guess that it's about an 8 microgram correction on a platinum iridium prototype with about a 6 microgram uncertainty. That seems to be the range that people have for the sorption value. So it's not too bad if you just had to guess. So the interesting thing is when you do measurements in vacuum, you have no buoyancy correction. Traditionally, the buoyancy correction has always been one of the biggest contributions to uncertainty in mass metrology. When we used to have the IPK, we were effectively realizing mass with a platinum iridium cylinder that had a small volume, and we had to compare it to stainless steel masses that had a big volume. And that volume correction uncertainty was related to the magnitude of the volume difference, as well as your air density uncertainty. And so that was typically at about 98 milligrams correction and about a 9.8 or 10 microgram uncertainty. So if you can get air density to about parts in 10 to the minus 4. Now we can typically do a correction from sorption. You can replace this by doing it doing the comparison in vacuum and say using stainless steel sorption artifacts, bringing them to air. You don't have to do buoyancy correction anymore when you're comparing those stainless steel artifacts that were calibrated in vacuum with 0 buoyancy correction. So you're effectively trading buoyancy correction for sorption correction for the most part. All you have is a little bit of residual differences between your masses, stainless steel masses, but that's very, very small. The center of mass that you have for your artifacts depend on the height. And so it is not fairly important to understand what the gravity gradient is in your measurements, because the center of mass needs to be corrected for the mass needs to be corrected for the center of the gravity gradients and the center of masses. So what we do is once we have those masses in vacuum and we brought them to air, we can then store the value that we've realized in the Kibble balance in a mass that we know the history of and we know the physical drift of. So this is how much we expect the mass to physically gain weight in time just through the accumulation of hydrocarbons or molecules on the surface. And there's pretty good models for that. I think the BIPM calculates about 1 microgram a year. Ours is a little bit higher than that, but we have a pretty good history of that, and it's got a root T dependence. So it changes linearly with root T in time. But we can store our realization values in that. So this was the BIPM calibrations before 2019. And it's effectively continues with the BIPM as maintained unit now. And we have our realization values here. And this is the change in the mass scale that's resulted from the consensus value calculation. So we've shifted the scale. So this is what the values would be with respect to the consensus value. Okay, so we have our value of mass. We can disseminate it out into the world. I'm going to shift gears and talk a little bit about the gravity requirements for the Kibble balance. And so gravity, this is the Kibble equation. In order to get mass, you need, of course, to measure the gravity that needs to be divided out. And that gravity is just based on the gravitational attraction of the Earth. And you can see here, this is from NASA Visualization Studio. It's, I guess, from the GRACE satellite. And there's variations across the world on the order of 100 milligals. And a microgal is about 1 part per billion. So as you can see, where there's mountains, you tend to have higher gravity, as you'd expect, because there's more mass there. So what we want to do is be able to measure gravity, and the way you can do that is through absolute gravimeters. The two commercial ones available are, well, there's multiple, but the main absolute gravimeter is this Micro-G FG5, which just uses a falling retroreflector and measures the acceleration with an interferometer. And this is a quantum gravimeter, and there's now multiple quantum gravimeters under development. And this is one, and this uses the free fall of an ensemble of cooled gas and measures the acceleration with an atomic interferometer. This one has drops of mass, and so it's good for measuring periodically, but it's not good for measuring all the time. This has really no moving parts, so it's more likely to be able to measure over longer periods, and also has a higher frequency of measurement because you don't have to drop, bring it up, wait for things to stabilize and keep going. And so it doesn't wear out as much either. So the quantum gravimeter has been under development for quite some time. The FG5 is effectively the de facto standard for absolute gravimetry. There is just a key comparison in 2023 that was piloted by NIST, and the agreement amongst all of them are pretty good. So some of the ones here that don't have an FG5 on them are quantum or atomic gravimeters. And the agreement has been about within plus or minus 4 microgal, so it's pretty good. If you want to measure long-term changes, so changes where you have a high resolution, you can monitor for a long time. We can use relative gravimeters, and this just measures changes in gravity, which is quite important. So this is a superconducting gravimeter that just uses magnetic levitation of a superconducting mass, and then these are based on deflection of a quartz spring. So this is the long-term measurements from the Canadian Absolute Gravity site. This is about 30 kilometers from NRC, where our Kibble balance is. And they've been monitoring it using various instruments for quite some time. The main one is this superconducting gravimeter that provides these curves here, but this black one is the model that they've been working on developing, which aggregates all the data that they have. They stopped using the superconducting gravimeter a few years ago and have bought this 𝐺phone X as a substitute. Initially, it wasn't in great shape, but it's giving better results now. And this is the AQG measurement here, which is the this is the atomic gravimeter they've just purchased, and it's giving reasonable results. But you can see there's variations in time, and this is seasonal variations. We'd like it to be periodic. It's not perfectly periodic, but there's definitely some periodicity to it. And at the Canadian absolute gravity site, they find about max deviation is about 6 microgal from peak to peak around on this, or plus or minus. And there's this long-term downward trend. So you can't just measure it once and then you're happy for the next 10 years. At least at at least in the area we have this post-glacial rebound, which is the glaciers receded. Now they had been compressing the earth and now it's coming up. And so the gravity is going down in time. And we see this also at the Kibble Balance site. This is just measurements using the FG5 gravimeter. Excuse me, but the rebound is different. And I'm not sure if this is from the elevation or just the different location, but their elevation is much higher than us. And so there's some variation there. But if you just took the standard deviation of our measurements and predicted something across the years, you could do that to about 2.4 microgal, but really you'd want to consider the max deviation on there, which is about 7.8. Now, if you take your absolute gravimeter and just put it in your laboratory, you'd measure daily variations in time. And this is what the signal from our absolute gravimeter looks like. And we can model out these deviations in time, which will give us something like this. And these are well-known, well, these are tidal models that have been developed. There's quite a few that are available. We use the one from Tamura from 1987, and there's been updates to that and so on. And these models, some of them can be found at this Eternal website. But the tidal models are made up of the Earth tides, so the motion of the Earth, the impact of the sun and the moon on the Earth, and that's the largest contributor to the daily variations. But it's also fairly predictable. The ocean loading is the response of the ocean to those tides as well, and that's harder to predict. And so the uncertainty of those is actually a little bit higher on the model, or the biggest contribution to the uncertainty of the model. But overall, the model is pretty good to less than a microgal, usually 0.1 microgal or better. There's also the polar motion corrections, which is related to there's a wobble that the Earth's axis has, and that needs to be corrected for. And also we measure the pressure above the balance, because the air column has a gravitational attraction that depends on the amount of air above it, which is dependent on the pressure. And that's typically about a 0.3 microgal correction per millibar. What we need to do in our Kibble balance is we actually use these tidal predictions to affect our servo motors. So for example, when we're doing our mass loading, we can predict what the coil current needs to be to properly transfer our mass. And so that does things more stably because it knows what to expect. So the ocean loading here is, this is the contribution to ocean loading separated out from the tidal models. And that's just about plus or minus 2 microgal or so. This is the pressure correction, and this is the polar motions. So we get the polar motions from this IERS website where they do these calculations for monitoring. So now the hard part is we think we have a good idea about what our absolute gravity is at a particular location. At NRC, we measure our absolute gravity at one particular pad here that's monitored in time. But we need to transfer that to the Kibble balance to hit our mass pan, which is just about here. Here. And so we need to know exactly what that is. And so how do we do that? Well, the easiest way to do it, if you're fortunate, you can just take your relative gravimeter, CG5 or CG6, and measure the difference in the gravity between the location where your absolute measurements are to the weighing position. We had a hard time doing that initially because the CG5 is sensitive to the magnetic fields of the Kibble balance, but we were able to shield that and we were able to come up with a value. But initially what we did is we did a lot of modeling. And so this is what you can do. And so what you really want to do is you can measure your gradients on your pads and you can measure the gradients across your laboratory. And before the balance is put in it. Because what happens is the balance itself has a self-attraction and you need to model that out to figure out what the impact of the gravity is going to be. And so we measure the gravity gradients across the laboratory. This is where we measure, the whole laboratory has been measured across this square matrix you can see here. And we also measure the vertical gradients. This is just a 3-position tripod where you move the gravimeter up and down. You can measure the height gradients as well. But then that gets mapped. And then there's a few ways to measure determine the self-attraction of the balance itself. This is Jacques Liard did this at NRC, and this monitored, measured the, modeled the gravitational changes due to all the components of the balance. So what you need to know is you need to know dimensions of the balance, you need to know the densities of the components to figure out what the distances between them and the contribution to gravity. As you can see, for us, our magnet is very heavy, and that's the biggest contribution. That causes about a 25 microgal shift from the balance-free gravity. And this was done using a technique referenced here, which is more like an analytical technique. Dr. Li, who gave a talk earlier today and did this work at BIPM with Franck as well, where they had an FEA model where they used the equivalent electrostatic form equation, and you could just put in your model and do some calculations based on the electrostatic equation and make some substitutions, because that equation looks very, very similar to the gravity equation that you'd want to have. And so those that work has been modeled so they can predict the value for their BIPM balance. Okay, so in summary, I suppose we talked a little bit about the 3 phases or the 3 steps for disseminating the mass from the Kibble balance out to the world and the kind of things that you might need to worry about for your masses. Talked about the pressure minimum that you want to have to operate your balances. And typically that's easy to get anyways. Most of the balances run well below that anyways these days. And then how to do the vacuum transport from vacuum to air to disseminate out to clients, and then various aspects of the gravity. So with that, I want to thank everybody, and let me know if you have any questions.
So the next speaker is my colleague from NIST, Darine Haddad, and she has worked in her life on 4 Kibble balances already. So she's a pro. She did her education at the University of Versailles, not far from here. And then she moved to LNE, where she worked on the LNE watt balance at the time, now Kibble balance. And then since 2007, she came to NIST, originally working on NIST 3, then on NIST 4, and now in CHEMS.
Great, thank you, Stefan, for the introduction. I'm going to talk about the mechanism and alignment in my talk. I thought we had 15 minutes, so my talk will be very short. So we'll be out of here very soon. But we have another hour to have more discussions later. Which? Oh, it's not advancing. Oh, here we go. So in all Kibble balance, one has to think about their guiding and their balancing mechanism. And In the balancing mechanism, it's supposed to do comparison of forces. And for the guiding mechanism, the purpose of it is to define the trajectory of the coil. And both guiding and balancing mechanism, they have to support a certain load in your experiment. So there are different ways, and different group of Kibble balance have chosen different ways to do guiding and balancing mechanisms. If you look at the to the A, guiding and balancing mechanism, they're both combined. And this is a strategy that NIST have used in all their Kibble balances from NIST 2, NIST 3, NIST 4, and in CHEMS as well. NRC Canada also have combined guiding and balancing mechanism, and then NPL as well, the old one and the new one, and PTB and Ilmenau and MSL, they use combined guiding and balancing mechanism. And in that case, the magnet is fixed. And in B, this is the strategy that Eleni and Metas and Chris in their first design, where the guiding mechanism is fixed and you have a balancing mechanism attached to the guiding mechanism. And the balancing mechanism can be either they made their own balancing mechanism, or it could be a weighing cell that you can attach to a guide, and you move your balancing mechanism along with your coil. The coil is attached to your balancing mechanism and the magnet is fixed. There's also another way to do things with a Kibble balance where your balancing mechanism is fixed and your guiding is attached to the balancing, and you can move your coil with your guiding mechanism. Magnet is also fixed. That's the BIPM strategy. Nim and Ume and Tsinghua University, they have a weighing cell, and their magnet is actually moving. So the guiding is installed on the magnet, and you're moving your magnet. There's also University of Ilmenau, I believe they're working on a modified 1 kilogram balance where the coil is attached to a guiding where you can move it, but also you have a balancing mechanism where the magnet is attached to the balancing mechanism. For the rest of the talk, I'm going to be talking about A more because this is very favorite strategy because it's much easier to cancel some common biases. And Kibble and Robinson demonstrate that in one of their paper, and I'm going to talk about it. This is an important factor to consider. And it's also reduced the amount of parts you have in your mechanism. So, you know, when you want to build your Kibble balance, you want to minimize the amount of parts you have to minimize the sources of failure. And it's much easier to operate and maintain because you have less parts. So as I said, I'm going to be talking about option A for most of my talk here. And you have two options when you're, so far in literature, you can find two options. Either you can use a wheel, like a pulley to do the balancing, or you can use a balance mechanism to do the weighing. I feel like I skipped one. Okay, I'm missing one slide, but okay. So you can choose one or the other. Each one of them has advantage and disadvantage. In A, when you use a pulley, you mainly move along a perfect trajectory when things are well aligned. With a beam, you have some cosine, so you have an arc of motion when you move the beam. Now, if you want to make a 1 degree of freedom motion, you want to attach to those mechanisms some guiding to make sure it's moving along a perfect trajectory. And there are multiple choices in literature that you can use based on flexure design to guide the motion of the coil. In B, I'm showing a a folded parallelogram structure that with external linkage that we have used at NIST in the new generation we're building for Kibble Balance, which we called GEMS. Now, if you want to attach an additional guiding mechanism to your balance, there's a small advantage for the wheel over a beam. And the reason for that is with a beam, because of this arc motion, you have those horizontal forces. And if you try to calculate the total stiffness of the mechanism using Lagrange formalism, you can see you have a very large nonlinear total stiffness. So for this particular application, the wheel has the advantage if you want to add an additional guiding mechanism. Now, in most Kibble balances, you can see we always compare the forces on the same side. And the reason for that is you want to make sure that your lever arm doesn't change. So you can see the gravitational force is always compared at the same in the same location as the electromagnetic force to align the forces really well. If you don't have that, of course, you have to take care of the lever arm changes. For tabletop, maybe it's fine, and we've seen some presentation. If you want to do to 10⁻⁵, that's probably okay. But the reason I'm mentioning it here is to show that it's important to understand that in a Kibble, when we do the equivalent of mechanical and electrical power, what we need to measure is the velocity of the mass. Because all the time we talk about the velocity of the coil, but it's the velocity of the mass needs to be measured. And what we do is we use, in high accuracy Kibble balance, we use those double gimbal as a proxy to compare those forces. And here I'm showing you like this very simple calculation to show you that why is it the velocity of the mass? Because if your mass is here and you're comparing mg_L2 times is equal to BLI L1 because your force is here. And then if you move the coil in the same magnetic field in here, BL is U/BC. And so mg, the mass, the gravitational force here, times the velocity of the coil times L2/L1. And this velocity here is the velocity of the mass. But because we have L2 equal L1 in Kibble balance, and we have those double flexures, then the velocity of the mass is equal to the velocity of the coil. Now, for the pivot, in literature, there are two things we're using. We're using knife edge. Most of the Kibble balances that I presented in option A have traditionally used knife edges. And the reason for that is because you can suspend tens of kilograms of load. Like NIST2 and NIST3 were like about 50 kilograms. And if you want to support less, if you have less load, then you can afford to have, to use flexures. But most modern, like mass comparators, they use flexures. So, and it's easy. It's easy to do flexures because you can machine it more easily than having to build knife edge and flats. And you can also have very large deflections with a knife edge. So if you want to move if you're using the same mechanism and you want to move the coil, you want to have large deflection of the beam or the wheel, then the knife edge has the advantage. The knife edge, though, has hysteresis, substantial hysteresis, because you have plastic deformation. There's a line contact between the knife edge and the flat. But the good thing is that this hysteresis, you can erase it. And we have seen multiple talks here today. Pastor Day is talking about erasing of hysteresis. The hysteresis in flexure is smaller, but you have another effect, which is anelasticity. if you want to think about it, it's kind of like hysteresis is kind of like a constant offset, but anestheticity is a relaxation effect. So the good thing also about here, we did some studies at NIST, and you can also erase that. So in either case, you can erase those terms. So now let's talk about the suspension. The suspension of your mechanisms to suspend the coil can be either stiff, like in A, and so far, most of tabletop Kibble balances, they use stiff mechanism. The advantage of that, of course, you don't have any swings of the coil or the mass band that I'm gonna show next. And this is very good if you're doing a BIPM measurement, so because it's much simpler. The only thing that you have to worry about is how can I measure and adjust my Abbe error in a stiff mechanism. And also you're very sensitive to off-axis loads versus all the high accuracy Kibble balances, they use gimbals. They're different kind of gimbals, either one single flexure or flexures in series. D is what NIST is using. And the reason why we have that is because you can clearly separate horizontal motion or forces on the coil versus torques on the coil. The disadvantage, of course, you have those oscillations whenever you have forces and torques on the coil. So this is showing the equivalence between mechanical and electrical power in 6-dimensional case. And in Kibble balances, what we try to do is we try to minimize those 5 other degrees of freedom. So you can, if you can design your system to have no forces, then it's perfect, or no horizontal velocity, then you're good, or you try to minimize them. And this is what we do. We try to minimize them. You don't have to make them 0. They have to be small enough so their product is small. Now I want to talk a bit about the Kibble-Robinson theory. We started calling that at NIST like about 2 years ago, KRT. So if you have the same guiding and balancing mechanism, which is the way that NIST has been doing in NPL too, and there's a big advantage to that is that you can write the velocity. So in the equivalence between mechanical and electrical power, the electrical power is scalar, but the mechanical power is a vector. So the force is a vector and velocity is a vector. But if you can write them in terms both velocity and the force along a single vector, you can see here that when you combine them, things can drop out. So all these error bias terms that we had, they drop out. And now going back about to the mechanism, the way we suspend mechanism to see which one follow KRT or not. Most of like tabletop Kibble balances, because they chose to do, if you choose to do the same guiding and balancing mechanism and you make it stiff, that follow KRT. And the mass band here, I want to mention, because we have seen some mass band are suspended below some mechanisms, sometimes the mass band is suspended above, so but it's the same. It has an advantage, you have no gimbals, so there are no swings. But you have to be careful because you're sensitive to off-axis forces because of where you place your masses, so you'll be sensitive to that. The second one is it actually follow KRT except for when you have all the suspensions also when they're not stiff, they're compliant. if you have the same guiding and balancing mechanism. The only difference is that in KRT, they describe to have a stiff suspension of the coil. So in that perspective, it doesn't follow KRT. But this one has the advantage of like you can properly align the biases. So there are no force and torques on the coil. And then you have what you have similar to mass comparator, where the mechanism is stiff, but you have to suspend your mass band with a gimbal. And I think this would be for the future, that would be the best choice going forward. At NIST, when we build chems, we build it according to B, but there is a possibility to actually stiffen all these flexures to make them stiff and be in the C configuration. So you can go back and forth between them. And the advantage would be is you can make your suspension compliant, so you can align the coil and the magnet so you don't have extra forces and torques in the coil, and then you stiffen them up and you'll be in this configuration. Because in this configuration, you don't know where you are. You don't know where your coil is in the field, and those forces still exist, but you don't see them if your system is infinitely stiff. So I think KRT is a great way to go for the future, but you still need to consider some error. It doesn't mean like I don't need to align anything because you still have some error in velocity. And most of us, to measure velocity, we're using laser interferometry. And the first error that you have is a cosine error. And this does not depend on the motion of your retroreflector, of your optical target here. It depends on your misalignment of your laser beam. But you also, if your optical target is also have horizontal motion, you also have a sine error in addition to the cosine error. And that error depends how misaligned is your laser beam and how much is the motion of your optical target. So just to give an example, so if your laser beam is aligned by 45 microradian, which most of us can reach, we can reach this, this value with cameras and telescope, or and then if your motion is, say, 1 micrometer, your optical target as you're moving, your guiding can do 1 micrometer over 10 millimeter travel, then your measured velocity in relative is reduced by 1 ppb. So if you want to do 1 ppb on your cosine error, you have to align to better than 45 microradian. And your sine error would be 4.5 ppb. So the more you minimize the optical target motion, or you can drive this one closer to 0 to minimize this error. So here I'm showing 2 ways if you want to align your laser verticality. Most of us use a reference liquid mirror. If it's possible, you can insert it. At NIST, we use an alcohol pool. We use silicone oil as well because it's quieter. And you can build a telescope and you can look at the motion. You can align your beam to vertical using a camera. Metas, I saw them yesterday. They presented. Sometimes you cannot put a pool in your experiment. So what you do, you can use an autocollimator and record the position with an alcohol pool, and then you can use a transfer mirror. You transfer the value to a mirror, and then you can transfer this mirror to your experiment to align the verticality. The other error that comes in because your optical target is moving is what's called beam shear error. And this beam shear error depends on your beam size, which is called D beam here, and how well is your reflector, and, surface imperfection in your reflector. And today everyone can get lambda over 10 surfaces. So as an example, I'm gonna say again that your optical target is moving because your guiding mechanism is moving this way. It's 1 micrometer over 10 millimeter. And say you use red laser with a beam diameter of 3 millimeter, the beam shear error is 4.2 ppb. So you have to consider that when you have motion of your optical target. You also have to consider the Abbe offset, which is a misalignment between your mechanical axis and your optical target. If you have an Abbe offset, I'm calling it here delta E. If you don't have any tilt of your optical target, then you don't have an error. But if you have tilt, and this is an example, say over the whole trajectory of 10 millimeter, you have 10 microradian, and the offset is 200 micrometer. Say, because this is machine tolerances, you positioned it there, and you got 200 micrometer. The offset can be 200 ppb. But even if you don't, so you have two options: either align it or you can measure it. So if you measure this offset, then you can take care of it. You can correct for it, and the uncertainty could be sub ppb. So you need like a micrometer knowledge of where your optical target is with respect to your mechanical axis. And finally, I want to say that I'm going to repeat what Michael Jackson said: you're not alone. The Kibble Balance community is very large. I'm talking to people like who's starting to build Kibble Balance, and everyone here is eager to help and answer any questions. And this is the new Kibble Balance at NIST GEMS, which will be ready next year. And our plan is to publish it on GitHub next year. So everyone will have access to all the hardware and all the software. I can't promise everything will be there next year, but we're going to have a large portion of it. And those are my colleague, Franck Seifert, and me. This is during Franck's visit at NIST. And this is Lawrence Keck. Most of the things that I talked about today, he did his PhD thesis at the University of Illinois, and with us at NIST, so most of the stuff is available. So you can go back and have more details about it. I think that's it. Thank you.
All right, we're moving on from mechanical stuff to electrical measurements. And it's Ian again. And we have already heard the introduction of Ian Robinson, so I'm not going to introduce him again. But, Ian has a lot of experience because he worked with Brian Kibble on many of the electrical metrology techniques, and he has the fiber optical ring. And I think we're going to learn a lot about the electrical measurements from him.
Probably not the talk. I've tried to make it so it's not specific, but I will just talk about ways of doing things, because otherwise it would just be trying to describe what I was doing. Oh, okay. Well, good afternoon, everybody. It's me again. So, okay. I'm going to talk about electrical measurements, but I'm going to try and make it reasonably general because I don't want to describe the sort of the NPL way of doing it, but I will say things about that as well. Okay, right. Where's the? I've got it. Is it? I'm off. Right. I thought I'll also talk a little bit about the about industrial level balances as well as the other one, but not very much. Because effectively for industrial level balances, the problems, if you're working sort of at uncertainties above 50 ppm, it's surprising you can do practically anything you like. And conventional electrical standards will allow you to make electrical measurements really quite easily. But generally what you want to do is keep the costs down. But as your uncertainty requirements go up, then conventional standards seem to run out if you also if you want to keep the cost down, it's very difficult to do that. Right, I'll try and cover a reasonable range of things. Am I there? Yeah. Okay, I'll start off with talking about the weighing. I'm assuming that everybody knows what a Kibble balance does. So in a conventional balance, you balance the weight mg of a mass m against the force generated by a current flowing in the coil. And you pass that current through a resistor R and measure the voltage V. If we want a high precision measurement, obviously we've got to use a 4-terminal resistor, and to avoid errors due to the lead resistance, that's fairly straightforward. Also, we arranged to make an offset in the things of m/2, so that the mass is measured as a difference between equal and opposite currents. A number of people have said why we do that for certain parts of the balance. For the electrical part, so that we switch between plus I/2 to minus I/2 when the mass is removed or added. One of the reasons is that for a resistor, that means that the power is constant in the resistor for both parts of the balance. And that means that if it's an ordinary resistor, it will have a power coefficient, and that power coefficient is constant between the two parts. It makes it easier to do the calculations. Also, if we get that right, the linear part of the effect of the current on the magnetic flux density is eliminated as well. So in some balances, you adjust the weighing current using a servo system to keep the balance at a designated position. In others, other people have talked about the current is kept constant and the force differences are monitored by a mass comparator. So there are two ways of doing this. No matter what you're doing, in the end, you've got to be able to resolve changes in the weight of the mass to a few parts of 10 to the 9. So what you need is a low noise current source, precise low bandwidth voltage measurement, and a stable resistor. And also the servo must be carefully designed to minimize the effects of balance drift and external vibration. So, but you can, some advantages can be obtained if you adopt a variant of the approach originally suggested by BIPM. This employs a couple of separate coils. We've talked about this in the past, but two separate coils derived from either a twisted pair or a bifilar winding, allowing one coil to carry the weighing current while the other can be used for the moving measurement. It has a number of advantages. In one case, the weighing current flows in the resistor at all times, which means it stabilizes, its temperature stabilizes, its power coefficient, everything is stable effectively. Whereas if you're doing the other form of balance, when you go into moving mode, you turn the current off in the resistor, so it cools down. This means you've got a much more stable system. And also, you can measure BL with the mass up or with the mass down, and no assumptions need to be made about the effect of the current on the magnetic flux density. There's also another advantage in that effectively this KLT can be applied to those two different kind balances, because effectively the alignment of the balance will change when the mass is up or mass is down if you're not very careful about it. So moving on to the moving part of the experiment, the coil is moved up and down with a measured velocity, and the voltage generated is measured. So in a conventional balance, it's done with the weighing current removed, and the BL product is applied to the weighings, both with the mass up and the mass down. But you do need to know that that BL product is effectively that it hasn't been affected by that linear the linear effect of current on magnetic field. Otherwise, you'll get an error. In the two coil balance, you can just use the appropriate measurement of BL with either the mass up or the mass down. So you don't have to have the two currents equal and opposite if you don't want to, but it does, again, as I say, it helps for the for keeping the resistor at and the resistor power coefficient correct. And as we've seen in our other talks, the ground vibration actually generates a lot of significant noise in both the velocity mode and the voltage signals. However, the noise is correlated, and with care, you can get rid of the noise in the measurement results. We've seen how Franck's already described how that is done. But one of the things that wasn't really gone into was the bandwidth of the measurement channels. That's an interesting subject. Effectively, the interferometer channel has a very high bandwidth, but the voltage channel doesn't necessarily have a very high bandwidth. And so what we do is we try and measure the two over the same time. However, the velocity signal, it's got a limited bandwidth, so you can't necessarily assume that the two signals will be the same at all frequencies. And so effectively what you want to do is to try and ensure that your voltage circuit has enough bandwidth to cover the point where until most of the signal disappears. And that normally occurs above a few hundred hertz. So it is very nice to be, or it's essential to have a nanovoltmeter that has a high bandwidth. If this only occurs in watt balances, in the dual balance, you halt the measurement, so you don't have these bandwidth issues. So put some values on the whole thing. If we want to weigh half a kilo with a BL product of 500 Tesla meters, we end up with a current change of 10 milliamps, a voltage change of 1 volt. If we want to part in 10 to the 9, we need to measure a nanovolt. So the basic device has to be able to get down there. But vibrational noise is present in the measurement, but we can measure over extended periods. So effectively, we can average and get down towards our nanovolt target. But when we're moving, if we're moving at a millimeter a second, we get a volt out of the coil, or difference in voltage of a volt. But there's a vibration of maybe normally something like a micron a second. So there's a millivolt of noise on the thing, and you saw that in some of Franck's data, that there's quite a high noise, but you still need a nanovolt. And if you try to average down from a millivolt to a nanovolt, you're not going to do it, not in a sensible time. So you need to use the correlation between the two, and as we saw before, that is possible. But again, as I say, we need to at least ensure that the correlation is correct over the time we're doing the measurement. So you need a good nanovolt amplifier. The other thing that we need to think about in these measurements is that we want to try and achieve uncertainties of a nanovolt per volt. That is pretty difficult. And really, we need to ensure that the instrumentation is isolated. This is that Stefan talked about the optical fiber data bus that I developed a long time ago. That was intended to handle the isolation of all the parts of the apparatus. So effectively, the problem with many voltmeters and things of that sort is not only do they measure voltage, they also generate currents. And so if you connect them together, they will influence other parts of the circuit, and you don't want that to happen. So it's important that the instruments you've got, you understand when you put them together in a complicated system, they don't generate second or third order problems. So you do that by isolating the devices from power supplies, so that your power supply isolation is good, both from from a point of view of DC isolation and also AC isolation, you don't end up with 50 hertz currents or 60 hertz in the States going around the place. And also the data connections don't cause problems as well. It's also very wise to keep mains power sources away from sensitive parts of the balance using DC power distribution. It was quite interesting. We were testing the new nanovoltmeter, and the guy who was doing it said, "Look, there's 50 hertz on this thing," and so I sort of moved the oscilloscope that he had near it, and the 50 hertz was changing. Effectively, it was just the magnetic field from the transformer of the scope was getting into the amplifier. It's very important to keep these AC fields away or to stop them, but it's hard to stop them getting in. So I'm going to go a bit into the voltmeters, how they work and why you need particular sorts of voltmeter. So the main voltmeter measures voltages in the weighing and the moving phases. We normally choose to use an integrating voltmeter as it gives a good noise performance and it's straightforward to use. I think Franck has discussed quite a bit about the Keysight 3458A and how that's used. But I want to talk a bit about charge balance voltmeters. Unfortunately, the Thaler ADC 180 is about the only commercial voltmeter that used charge balance techniques, and you can't buy them anymore. So we're building one. It was interesting that NIM in China, they're building the same sort of thing. It's I think once you've seen how they work, they're very, very nice. So the multi-slope voltmeters, they work by effectively charging a capacitor from the input voltage for a fixed time, and then you reduce the integral to zero using a series of fixed currents, and that measures the input voltage. But obviously, as we said, they are only sensitive to their input during the integration time. They're extremely versatile. They're very linear, and they have good noise characteristics. They're very impressive voltmeters. But that lack of sensitivity means that you've seen many people say you've got to use 2 of them or 3 of them even just to measure 1 voltage, especially if you want to make best use of your measurement time. It's quite important to measure all the voltage, not just 1 and then wait for a gap. So, and you've seen how Franck just described that. Now, the charge balance voltmeter works in a different way. The input is integrated all the time. It's never disconnected. And what happens is a reference voltage is switched on and off for timed periods to keep the integrator switching between 2 fixed levels. And you can then read the voltmeter out when it reaches one of those 2 levels. So you can't read it when it's in between, but you can read it at the end. And you normally switch it around, they normally organize it so it switches around the few hundred microsecond level. And all you're doing, all the voltmeter is doing is counting up the amount of, say, positive reference and the total time it's doing something. And it returns, you get the different, you trigger it once, it returns you some values for those counters, trigger it again, you get the counters again, and the difference gives you, and you combine the 2 together, and that gives you the voltage. So you can have very short sample times and very long sample times, but the one thing you can't have accurate. The trigger can be delayed by about 200 microseconds by the time you get to a point where it can report its value. But remember what I was saying about effectively about the frequencies from the frequency of the vibration going into the apparatus. As long as you're effectively there's no energy in the signals, then a few hundred microseconds of trigger error isn't actually going to change things at all. Also, anything that you don't measure in one period goes through to the next one. It never stops integrating. So that's the thing. We have to and in the case of the multi-slope voltmeter, you've seen Frank gave a great description of exactly how that voltmeter triggers the counters. For the charge balance, the trigger signal is generated by the counter at each edge of its gate, and the voltmeter then stores the state of its counters at the next available time. So you've got you've got some jitter on that, but as long as the energy in the voltage signal is is negligible at that sort of frequency, you don't really care. So that's that having an approximate one is perfectly good. So if you're going to measure these voltages, you need to use a Josephson effect voltage reference. And nowadays, almost everybody uses programmable Josephson arrays, which allow you just to get a volt. You can just say, I want this voltage, and it gives you that voltage. And so some people use that array to calibrate their conventional voltmeters really rapidly, so that they can use ordinary voltmeters directly to measure the coil voltages or the resistor voltages. But another approach, which I happen to like, is to use the reference to oppose most of the voltage from either the resistor or the coil, leaving a small voltage which you can then measure with a reduced. You don't need to use a higher uncertainty to measure that voltage. This allows you then to, rather than just measure with an ordinary voltmeter, you can use a nanovolt amplifier to amplify that difference voltage before you measure it. So effectively, that gives you a real advantage. However, most nanovolt amplifiers have a limited bandwidth, which means that when you're trying to do this correlation for the moving part, it's not going to work very well. For the weighing measurements, it's fine. But what you can do, and that's something that example of the nanovolt amplifier testing was actually building a nanovolt amplifier that has a wide bandwidth. If you take a conventional amplifier and look at its input voltage with a nanovolt amplifier, you can generate yourself an amplifier with sort of kilohertz level bandwidth, but no 1/f noise. So you get the best of both worlds. It's more complicated than an ordinary nanovolt amplifier, but it gives you that ability to actually integrate properly over the moving velocity sample time and the voltage sample time. The other thing that you need to do when you're configuring these machines is to effectively check. You have to be able to change the signal paths in the balance. And if you're trying to measure at nanovolt levels, you need the switches to work at that level as well. And it's surprising how few people sell switches that work at this level. In the past, Brian and I made modified relays to, they were power relays with effectively copper contacts. What you did, drilled a hole in the back of the copper contacts, stuck a copper wire in it and hit it with a hammer. And that sealed it up, gave you relays that would switch pretty quickly at nanovolt levels, but they were horrible to make. And so really, if we're starting now to move into areas where the balances need to be relatively easy to maintain, and you can't do it with that sort of technique. So we need automated switches that don't produce large varying thermal EMFs when the switches are switched. So what you want is pretty much copper contacts, possibly gold plating, and what we're looking at the moment is to use effectively printed circuit boards so we integrate all the low thermal EMF circuitry on one aluminium PCB, and the switches come down onto them driven by solenoids. And means we should end up with an extremely good low thermal EMF switching system. But obviously, you can do that any way you like. And then we using shielded twisted pair cables with silver-plated copper conductors can allow you then to connect that switching system to the other parts of the balance. So the whole system keeps a low thermal EMF. Just going on to the weighing measurement, the current source, again, they need to be low noise and low drift. And it depends a bit on which part of your balance that you're using it in. You have to choose the level of drift that you can accept. In some balances, certainly the balance we're building at the moment, there are two. There's one for the tear coil system, and that effectively provides the moving drive and flexure stiffness compensation. And the range for that is small, so you can generally have a fairly small range current source, so you don't need to really push the drift hard. But that can also be used to offset the sort of the half the mass. And so that means the larger range, so you need to get the drift down so that it doesn't affect the data fitting at the end of the, if it's drifting fast and non-linear in a non-linear manner, when you do the data fitting, you can't get rid of it that easily. And the main source, it depends really whether you're using that in a servo loop or as a fixed current. If it's a fixed current, you need to keep the stability and the noise, high stability, low noise. Otherwise, you're going to compromise the measurement. In a servo, effectively, the servo is getting rid of some of your current source noise by adjusting itself. And as long as the noise of the current source is less than the noise that you see when the servo loop is active, you're fine in general. And so, okay, we need a resistor to convert the current to into a voltage. And so effectively, you've got the noise appearing across that resistor is mostly generated by the servo system, a little bit by the noise of the current source, but you could try and keep that low, and the noise of the resistor, again, both of those should be quite low compared to the normally to the vibrational noise. Now, most balances at the moment use conventional resistors, but it's possible to use a quantum Hall array, which is really rather nice. Now, conventional resistors consist of metallic resistance elements, and they're arranged to minimize imperfections. However, you always get temperature sensitivity, power sensitivity, long-term drift and instability, humidity, and sometimes humidity and pressure sensitivity and shock sensitivity. So they need a lot of careful handling, but if you do it right, you can get down to levels that below 10 ppb, which is good. But one of the important things, though, is if you are controlling the thing's temperature and you have to carry it from where you use it to where you're going to measure it, you need to ensure that the temperature control system and everything else does not change as you move it, because effectively, if that happens, you get a value at the calibration end, which is not the value used while you're measuring. And that is very difficult to find. So you need to think very carefully about how you're calibrating these devices. Obviously, if you can use a quantum Hall array, it's wonderful. They don't have any of the imperfections I just listed, but you have to be careful. You've got to ensure that the array is quantized. It operates at cryogenic temperature, so you've got to have a cooling system, and that generates vibration, so that's going to cause you some problems. And also, they operate in high magnetic fields, so that can compromise your magnet if you're not careful. And they're very expensive, but if you can go down that route, it is wonderful. Now, temperature control, I'll go into a little bit. Again, it's an electrical measurement. So a number of the parts of the apparatus may require temperature control. In our case, we temperature control the magnets, but also we have to to control the temperature of the resistor because we have a portable resistor, because our QHR is almost 1 kilometer away, so it has to be carried. And sometimes it's quite useful to control the temperature of the electronics, because, as I said, with nanovolt switches, nanovolt amplifiers, keeping them at a constant temperature removes a lot of the thermal EMFs in the system, which helps a lot in keeping your measurement noise down. So I just go a little bit into the sort of the weighing servo system, just describe some of the systems. The servo required for weighing depends on the mechanism you use for addition and removal of the working mass, because a number of balances use a physical stop, and so effectively you can use an ordinary PID servo because you don't have to act very quickly. However, if you don't want to put the balance against a stop, which could affect hysteresis and other things, and use the servo to maintain position while the mass is coming on, going off, you need to react very rapidly. And so quite often the best thing to do is to mutate the servo so it's sensitive to acceleration. The mass lands, it stops the mass within a few tens of microns. And then once you've landed it, the very noisy acceleration servo gets mutated back into an ordinary servo, which is much, much lower noise. And so just the data you're going to collect when you do this, it's normally, you want the resistor voltage in a weighing, which is derived from the voltmeter measurement, Josephson array settings, preamp settings. You need to log the time of the measurement. I use modified Julian date, so it's obvious how that is related. So nobody accuses me of using British summertime rather than anything else. So that allows us to lock to all the other measurements in the system. You get position data and other things like mass state. In the moving, going on to the moving measurement. So the aim of the servo for the moving measurement is to maintain the coil at the desired velocity. And it is possible, people have done this by just servoing directly to velocity. I tend to servo to a point that moves at a desired velocity, which allows me to get very precise motion of the coil. It will start at a particular point and stop at exactly the point I asked for. And that works, and you can get very gentle acceleration and deceleration. That's used, I think, I did that for the NLC. The NLC one has the same system. So a bit about measurement optimization. If you've got a nanovolt amplifier in use with the programmable array, you can be fairly sneaky. And if you take the velocity data from the servo and use that to set the array, you can continuously null the voltage from the coil, and you can keep the preamplifier connected between the two, and it doesn't overload. Otherwise, you have to disconnect the amplifier, reconnect it, and you've got nanovolt level transients all over the place, which will be bad. That's a nice technique. I'm also thinking of using the same technique for the weighing and effectively track the current, and that would allow me to keep the nanovolt amplifier connected from when you're moving from positive mass to negative mass. So that putting the mass on and off. And so that sort of technique can mean that your whole measurement system is much, much quieter and more reliable. Data collection on the moving, it's pretty obvious. Again, Josephson array settings, you need to collect the counter data that goes with the voltage measurement, time of measurement, and position data for start or end of the measurement. The balance state again. So it's like there's more data coming in on the moving. So in conclusion, it is quite difficult to get absolutely the best out of the electrical measurement systems required for the balance, but you can get very good results in lots of different ways, and a load of groups all get extremely good results for this. And you can get down to nanovolt levels in different ways. And in general, almost every problem on the electrical side has a solution. It's just really making sure that that everything is implemented correctly and you understand the whole system. So you know really what's generating a voltage, where any interfering currents can come, because it is better to have everything isolated properly so you don't get problems saying, oh, with ground loops and other things like that. There shouldn't be any ground loops. So and if you get to that state, you can be confident that the whole system is working properly, will produce low noise, accurate results. Thanks very much.